Okay, and that is that is a node of this dynamical system. Now, if you're on the red trajectory, the forward limit set is only 1 point. So here we have this point is a limit set, and also the closed loop is a limit set. And this, so we distinguish this point is in the big limit set, and we talk about maximal limit sets. So this limit set is not maximal because it's in a bigger limit set, whereas this bigger limit set is maximal because it's not, there's no limit set which is bigger than this. And so the nodes will be maximal limit sets. So once again, this is nodes and edges. Now, we are quite ambitious in this project in that we want to, in dynamical systems, we want to include things like diffusion reaction partial differential equations. And here is a Chaffee-Infante partial differential equation. So these are nicely behaved partial differential equations. Basically, they're diffusion dominated. And they were Fiedler and Roca extended their results a bit. This was first discussed in 1974, and then Fiedler and Roca said much more about the graphs of dynamical systems. And they weren't too specific as to exactly what they meant by a graph, but it wasn't very complicated. So these are all fixed points of the dynamical system. That is steady state solutions. And so basically, you have what's basically essentially a repeller. All of the edges of this top node go away from it, whereas these S's there are edges coming to it and edges going away from it, and edges going away from it. So this graph represents what's happening in this dynamical system. Now, of course, the partial differential equation is a infinite-dimensional dynamical system, but trajectories wind up asymptotically going to trajectories. There are, and at the bottom we have two attracting steady states of the system. So this is the graph of this partial differential equation. Okay. Now, when you saw a graph, what you know is that each of these nodes is a maximal limit set. But you don't know what that node is. It could be a chaotic set, it could be a periodic set, it could be a fixed point. You could label it if you wanted, if you figured that out. But this graph gives you a skeleton of what's going on, and it gives you an opportunity to find out more about the dynamical system. Now, Fiedler and Roca gave a number of other graphs, and some of them are quite complicated. For example, here is a graph. There are 4 attractors of this graph, a bunch of saddles, and these R's are top nodes. The trajectories go away from them. Here is a graph represented kind of a 3-dimensional plot of a different system, just to show you what these graphs can look like. Now, I'm going to show you, I'm going to tell you about the logistic map again. So here is the logistic map. It's a 1-dimensional map. And I hope that this bifurcation graph is familiar to some of you. That when you vary r between 3 and 4, you get a period doubling bifurcation. So if you pick a value of r and you draw a vertical line, that tells you what the graph is, what the attractor is doing for this particular system. Now, this is only showing you the attractor, and there's always, in this system, there's only one attractor. So your period 2 orbit becomes a period 4 orbit. Now, we know there are when you get period doubling, you go from a fixed point to a period 2 orbit. But we know that there are other things going on. For example, this fixed point actually continues on in this path along here, and but it's unstable, and this bifurcation diagram isn't showing you anything else. Now, this unstable orbit would be a node in our graph. As was mentioned earlier, I published a paper called Period 3 Implies Chaos in 1975 with Lee, Chen-Yen Lee, and we said, well, if you have a period 3 orbit, then there are lots of periodic orbits. So let me show you the theorem here. Now, this is small on purpose. This is one theorem, and it's small on purpose because I just want to outline what it says. Basically, if you have a continuous map and you have a period 3 orbit, so you've got 3 points, A, B, and C. A goes to B, goes to C, goes to A. That's a period 3 orbit. If you have a period, then there are infinitely many periodic orbits also simultaneously for the same value of the parameter. Furthermore, we said in this theorem that there's an uncountable set, call it S, on which the mapping is mixing, or we called it scrambled. It was a scrambled set. I won't define that, but I will show you another bifurcation picture. So I'm going to show you what happens in this little window. We call this a window because the activity seems reduced. So let's blow up this region. And here is a bifurcation diagram. And you will see at 3.83, you will see a period 3 orbit. And it's an attractor. But simultaneously, actually, Smale and Williams talked about this in 1976, that in addition to this, the periodic orbit, there is an invariant Cantor set. So here is, if you take a line, you can cut it vertically through this set. The red set is a Cantor set. And if you take a typical point in the Cantor set, its limit set is the Cantor set. So this Cantor set is a limit set. Almost every point in the Cantor set has a limit set, which is this set. Now, if you perturb ever so slightly, you're going to go away from the Cantor set and crash down to the period 3 orbit. So here we would say that there's a chaotic node, which is in this picture, it's a top node, and then there's a attractor node, which is the period 3 orbit. So it's a simple dynamical system. Now, what happens with these is as you follow this period 3 orbit, the dynamics are more complicated, and in fact, there's a window within a window here. And there are many windows, but this is the biggest one. And if you look carefully, there's a blue trajectory, there's a blue segment in here. Just as this one is red, there's the same kind of a thing going on inside here and it's blue. It's a chaotic set. It's a Cantor set, an unstable Cantor set, a Cantor saddle, chaotic saddle, and for these narrow choices of parameters, you'd have not just the red Cantor set, you'd also have the blue Cantor set. Now there are three pieces of this blue. They are the same dynamically active set. So the limit points on the blue set have a limit set, which is the blue set. Okay. So in 2021, Roberto DeLeo and I investigated what the graph of the logistic map is like. Now, the logistic map is so simple that it's possible to determine what the graph is like. And there's been a lot of literature on the invariant sets in the logistic map. Well, this is simply saying that this is the reference that Smale talked about dynamical systems in 1967. So now, what is the analog for the logistic map? Here we have periodic orbits and flows. Well, the logistic map is simpler. And we were able to prove the following theorem for the logistic map. Now, the graph depends on which parameter you choose. But I just showed you a parameter where there were three nodes, one red node, chaotic saddle, a blue node, chaotic saddle, and an attractor. Well, that's not the worst that can happen. There can be infinitely many nodes, infinitely many non-overlapping nodes, each of them a compact set. And what we were able to prove is that given any two nodes in the system, there's an edge from one to the other, but you can't go back. There are no loops in this graph. So any two nodes are connected by an edge. Now here we haven't drawn in all of the edges, I guess, but furthermore, these nodes, each node you can have, there's an uncountable set of parameters R for which there are infinitely many nodes. This is hard to picture. If you're interested in feedback control, these are ideal elements. Any one of these nodes, aside from the bottom one, they're all unstable, which means that if you perturb it a little bit, you can go zooming away and you'll go down to a lower node. But with a little feedback control, you're able to stay there. And as you see yourself drifting off, you use your feedback control to push it back on. So these nodes are also stabilizable sets. My most cited paper is actually on controlling chaos and how you can control chaos with small perturbations. So the theorem says that for every parameter value, this is a tower. Mostly, it's a finite number of nodes. But again, there's an uncountable set of nodes where there are infinitely many nodes. And if you have infinitely many nodes, there'll be a first node and a second node and a third node and so on all the way down, limiting down to the attractor. And the first node can be either a chaotic saddle or a periodic orbit. And the second node, same thing, can be a chaotic or periodic limit set, and so on. You can take any combination in this infinite number, and there will be many parameter values which give you that configuration. So this is the most complicated graph of dynamical system of interest that was ever published. And yet it's from the simplest dynamical system. So that seems a bit worrisome. Why is this? What we think is that many dynamical systems will have much more complicated graphs than this logistic. They might have something like this as part of the dynamical system. And so here's another way to draw the graph. So you have a top node, and then the next node, and so on, coming down to the attractor. And what we contributed was not the identifying these sets, but rather we identified the edges. We said if you start from one, you can get to any other one. That was our contribution. Now, so Roberto and I talked about how to exploit this. What's the next step? And we said, well, let's pick a dynamical system which seems very different from the logistic map. And one that many people might be likely to know is Lorentz system of differential equations. And so I'm going to tell you about the graph of the Lorentz system. Now, this is the set of differential equations, and three-dimensional set of differential equations, and this is a trajectory. And the we want to compare these. Now, rho is a parameter that we're going to vary, and Lorentz chose rho equals 28. But we're going to look at rho equals somewhere around 208 instead of 28. So first, we're going to convert it into a map. A standard procedure with the Lorentz system is if z is the height, and you take the plane at rho minus 1, that's the plane cutting across here, you can take a Poincare return map so that every time you come back downward and hit that plane, your point is recorded. And then you come back around and you hit it again. And then you come around and you hit it again. So that's the Poincare return map, is every time you hit the plane, z equals rho minus 1. And now we were able to choose one variable. I think it was x. I'm not sure. There's x, y, and z. And we made a bifurcation diagram, and we looked for places where it was similar. So here's a remarkable figure. So I've turned this upside down for comparison purposes. This is the picture I've already shown you. And over here in the Lorentz system, we're getting the same bifurcation diagram, where this is running from, I don't know, 208 or so, and 208.5 to 209.5, this whole scan. And you wind up seeing Cantor sets just as there are here, the red Cantor sets. You see the same period 3 orbits, period 3 attractor. Everything is virtually identical. So this is an example where this super complicated stuff that was going on in the Lorentz system, in the logistic map, apparently is also going on in the Lorentz system. And we presume that you would have nodes, you would have infinitely many nodes, just as you did in the logistic map. Now, there are differences. We do know that the Lorentz system is more complicated than the logistic map, and there can be additional nodes. So we're not claiming that the graph of the logistic map is a node, is a tower, but rather we're saying that it contains a tower. Now, this is just numerical technique. This is a rigorous theory. The logistic map is a rigorous theory, and this is based on numerics. because trying to prove what's going on here is too hard. So this theory is a combination of theory and numerics. And again, we have these crises occurring where as you follow the parameter to the left, you get sudden jumps in the attractor, and it's because there's a collision between two nodes. There's the red node and let's call it the black node, and they get closer and closer together and they collide at this point. And that causes a huge jump in the dynamical system. So Roberto and I are working on a theorem which says that so we asked ourselves about one-dimensional maps, more complicated than the Lorentz system. Is the graph connected? And so we worked on that for a while, and we came to the conclusion that yes, it is connected, but that's in preparation. Now, the logistic map gives you a certain picture. We've drawn the graph vertically with the attractors on the bottom, but Sheldon Newhouse proved in around 1980 that many maps, such as a logistic map or a force-damped pendulum, will have infinitely many attractors. And he emphasized that they could be periodic attractors, but they could also be chaotic. Infinitely many coexisting. So if you take something like a force-damped pendulum, you almost certainly, for some parameter values, uncountably many parameter values, there will be infinitely many coexisting attractors. And so what do you know about the graph? You know that the graph, well, each of these attractors is a node. You know nothing else about the graph. So our goal is to find out more about the graph. There has to be more. Once you know that the graph is connected, well, there are no edges that go from attractor to attractor because all the edges are incoming for an attractor. So you can't go from leave an attractor and go to another attractor. So that's a puzzle. That's a big puzzle. And again, these are the simplest dynamical systems. So here is a picture of Chirag will tell you more about these, I think. But so this is a force-damped pendulum, and I guess I should show you the equations. So here are the equations: theta double dot plus 0.2 theta dot plus sine of theta. I'll come back to this. So we have a force-damped pendulum, and it's periodic in theta. So theta runs from minus pi to pi. And so these two edges wrap around and are identical. You could roll it up into a cylinder, and this blue would match this blue, and so on. But what we have observed is that there's a chaotic saddle. If you start on the boundary of this between the different basins, there are three basins here. Basins are basins of a fixed point, and the basins' boundaries are terribly tangled together, interwoven. And if you start on the boundary, you stay on the boundary, but almost every point is in one of these three basins, apparently. That's not a rigorous theorem, but we don't see any other attractors. And so the graph would look something like this. So we have the chaotic saddle, and we have the 3 attractors. So that's the graph for this kind of a situation. Now, while Newhouse talked about infinitely many sinks, infinitely many attractors, they're not easy to find. And when I was working with Evelyn Sander, we made pictures of a series of the pictures like I just showed you, but we stepped it along in 0.01 steps in the parameter. So, and at 1.73, we found that there were 8 attractors. And here's what the graph looks like. What's going on here is that we know that, so these are fractal boundaries. We call these fractal boundaries because they are so interwoven. But over here, there is a boundary between the purple and the white. And on the boundary, there's a periodic orbit, a fixed point. That's this. It's a saddle. So you have the chaotic saddle and you have the fixed point saddle, and there are 8 attractors. Here there are 8 different basins with slightly different colors. And as I mentioned earlier, Chirag is developing numerical methods for finding these things, and the goal is to find them in higher dimensions. This is another picture of the same kind of a thing. And what you have in these dynamical systems is if you took all of the points in a box, they're all going to go map forwards. But suppose you take all the points in this box, a grid of points in this box, and you push each of them forward for one time cycle, Poincare return map, time 2 pi map, push it forward for time 2 pi, and the image of the whole square will shrink, and it'll shrink to about 1/3 as much area as it already has. And each time you iterate it, the area will shrink by another factor of about 3, and you keep on shrinking, and it comes down, but it also stretches. And so we have this very complicated yellow set, which is often referred to as a global attractor. Everything interesting happens inside the global attractor. Any periodic orbit has to be in this set where everything collapses down to. But in that set, you can have, according to Newhouse, infinitely many different attractors. And we think that you can also have infinitely many tower-like things. And so all of this is going together into a single picture that one has to try to tease out. So I think that there's a big opportunity to investigate the graphs of dynamical systems. Take dynamical systems, try to find out what's going on in these dynamical systems. So with that, I will quit, and I will ask if there are any questions. And by the way, here is we got this. This is 2 copies of the same picture, and that Evelyn and I made. Hello.
It was a grand lecture.
Thank you.
Graphs of dynamical systems were introduced. Even a simple dynamical system like a logistic map can have a complicated graph called a tower with so many nodes. He also compared the Lorentz system and the logistic system, their graphs of bifurcation diagrams. And he showed many pictures which helped us to understand how the attractors are situated. Are there any questions from the audience? Am I right if I say that
Who's speaking? I can't. I'm looking at the audience.
Yeah, I am Vinod.
Now, sometimes when you were talking, you were much clearer. That's much better. Much better. Hi. Yes, I think that's yes, but it doesn't go the other way. Okay, so you're absolutely right. If 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 they're conjugate, they're going to have the same graph, but the graph, for example, if you could have a dynamical system where there's only one node. Okay, for example, um, we don't plot the trajectories that come from infinity. So if you just have one attractor, it's a node, but you don't know what kind of a node that is. You don't know if it's chaotic or periodic or fixed point or quasi-periodic. So yes, you're right. And the goal will be to examine other dynamical systems and make this a goal of finding out how complicated these things are. There have been very few papers which are actually talking about dynamical systems. But as I said, it's been possible to determine what the graphs are for partial differential equations. So the field is wide open. Thank you. I apologize for not having been able to come to Kerala this time, but perhaps next time I will be able to come. I really enjoyed meeting the people in Kerala, and it's very delightful. It's almost a country, right? It's a state of India. Thank you. So I guess I will sign off. Bye.
Next plenary talk starts at 10:15. I thank Professor V. Kannan for chairing the session. Thank you, sir.
completed his MBBS from MOSC Kolanjeri, and after that he secured a position in the PhD in clinical neuroscience program through the ICMR-MD PhD talent search program. After his PhD, he did MD psychiatry in NIMHANS and also DNB in psychiatry. Currently, Dr. Isaac is associated with the Center for Brain Research as a faculty. Dr. Isaac's research interests are diverse, spanning clinical research areas such as neurocognition, neuropsychiatric disorders, geriatric giants, neurointerventions, geriatric advocacy, and social policy. His multifaceted expertise positions him as a valuable contributor to the field of neuroscience and psychiatry. So I welcome Professor Thomas Grigor Isaac for his presentation.
Thank you, sir. Good morning, everybody. First of all, big thanks, especially to Professor Vinod Kumar and team, and the international conference coordinators here for welcoming me and inviting me for this particular conference. Secondly, I would also like to thank Professor Sunny because he has given a very good kind of introduction to me. I'm not that big as in the introduction. So I'm just trying to be a person who wants to learn more, understand more, especially to bring about the kind of intersection between biology, mathematics, and by that I mean that it's bringing about more idea about the human data. And that is where we all stand together. So I would like to kind of bring greetings from my institute, that is the Center for Brain Research at the Indian Institute of Science. And I thought that I will kind of delve into some of the aspects, especially that brain imaging, how it can be used as a biomarker and how it can be used to predict and early detection of dementia could be possible. So these are some important aspects that we are working. It's not that we are working, we are the only team working. There are many teams across the world. We are one of them. We are kind of representing India in this regard. So here I thought that I'll tell about understanding the nuances of analyzing the structural brain images. So there are structural brain images as well as functional brain images. Previously in the previous plenary talk, it was actually told about the dynamic aspect. So dynamic aspect, we also try to look into moving systems, wherein there is fMRI, there is ASL, and these kind of image sequences, which are kind of analyzed and looked at in our institute. But I would be trying to concentrate more on the structural MRI, which is the structural imaging of the brain. For example, we go to a doctor and what do? They actually, so first of all, I have to give a disclaimer here that this is not going to be a talk on mathematics. I am a clinician and researcher with love for biological data analysis. That's my connection. So I would like to take that disclaimer and apologize to all of you beforehand. Now, I will also want to learn from you. Now, you see a clinician, what he does. You go to a doctor. You are telling that you are having a memory problem or you take a relative to a doctor. What they will do? They will do some basic assessments. They will ask you about the details. They will take history. They will examine you. They will make you lie down on a bed. Meanwhile, they will be also writing something. So the data is being entered the time you are entering the clinic. Then there will be also some kind of objective measurements. They'll be doing some kind of assessments. They'll taking your height, weight, the blood pressure readings, your body weight, and all other details also will be taken. Along with that, for somebody with a memory problem, they will also do what is known as neurocognitive assessments. So neurocognitive assessments, you would have heard people doing some memory tests in children, wherein they'll ask or they'll tell certain numbers. You have to remember that in serial order. You have to remember that in backwards order, so on and so forth. The reason for neuropsychological assessment is to identify how much is the capacity you have, as well as which area of the brain is likely to be affected if that particular test is getting affected. So different brain regions actually code for different brain functions. So that is something which is identified. And then the doctor will kind of give you a test write-up telling that you have to do so many blood tests or so many scans or so on. So then you go on for the different assessments. So this image, I'm not sure whether the audience would recognize. So this image is actually what is known as the CT scan of the retina. So we have the retina in our eye, and this retina has 10 layers. And this actually is the CT scan of the retina, known as optical coherence tomography. So what it does, it is able to identify any small changes in these nerve layers. Because retina is directly connected to your optic nerve, and your optic nerve is directly extension of your brain. So anything, any issues in the brain, you can actually look at your retina and can identify. That is one of the reasons why lot of assessments, lot of studies are looking at eye as an important area for looking at biomarker. Second is you also do some assessments, cardiological assessments. They'll make you lie down, they take your BP in sitting position, lying position, and so on. And you will also get what is known as heart rate monitoring, that is autonomic function. So this is something which is also being tested. Now the icing of the day is the MRI. So this is the fMRI images. You can see when the brain is at rest, what all areas are active, which is known as the default mode network. And when you give a task, what all areas are active, which is a task-based fMRI. There is another graph you can see here, is a person who is walking. So gait is something which is again coming into forefront, gait analysis. So gait is supposed to be signature. You can identify somebody with his gait only, isn't it? So people can mimic somebody based on his gait. So gait is like a fingerprint. It is individual. We can say that Mohanlal walks like this, Mammootty walks like this. I'm just telling an example. But these are the ways, and you can plot definite graphs based on the cadence, based on the stride length, based on the stance. So all these are independent measures, and you can identify that this particular person is having this particular pattern of gait. And it is found out that when you have dementia, or when you have beginning of dementia, there can be change in the gait. You would have also observed people who are very elderly. You would say that my father has become very slow. My grandfather has been not active like before. He is walking very slowly. These are all indicators that underlying dementia is there in the pipeline. And then we have the audiological assessments. That is again a clue. Now, a lot of you who would have heard of pure tone audiograms, which all generate different kind of patterns with different decibels of sounds which is given and response to that. So pure tone audiogram is another data. So I'm just trying to familiarize the audience to the kind of data which can be utilized to identify things, and especially using mathematical model methods, it is very easy to identify and predict the risk for developing a neurodegenerative disease like dementia. Now, I have some disclosures. I'm also kind of funded by the Tata Trust, and from the Welcome DBT Alliance, I'm part of some of the grants there. Now, coming to the aging brain and neurodegeneration. Now, why do we have to study all this? Can we just diagnose a patient and tell that he's having dementia? Or is it worthwhile to actually understand the person and identify the person who is vulnerable or at risk to develop dementia? Which is more important? The main aspect is you have to identify the person who is vulnerable to dementia, and that is very important, because otherwise you will lose the chance to intervene. Dementia, you know, there is no cure, no treatment. Many doctors will tell you do crosswords, you do some puzzles, you keep yourself mentally and physically active. But apart from that, you cannot offer much. But if it is quite early, like in case of cancer diagnosis, if you diagnose a patient with dementia, or even before he develops cognitive problem, you can actually manage. And with that management, his functioning can improve. So somebody who can develop dementia maybe at 60, you diagnose him with dementia at 60. But if you identify that he has a risk for developing dementia when he is 40 or 50, you can actually prolong that period of healthy life and actually delay the onset of development of dementia. So that is one important aspect. So pathogenesis of dementia starts few decades before the clinical disease manifests. So that is one important aspect. And why do we have to study dementia? Dementia is not a very big health problem, isn't it? We have fever, we have COVID, we have other issues to deal with. Now, why you are studying about a rare disease, or we have cancers, we have cardiovascular disorders, we have stroke. Now, why study dementia? The reason is our elderly population is growing. And most of the elderly population proportion is there in Kerala. That is one important aspect. We didn't have the census on 2021, but I am sure it will happen subsequently. But the previous census in 2011 showed that 11% of the people in Kerala are more than 60 years of age, and they are at a higher risk. And this is the important factor that actually is there, that there is an increased number of geriatric population. And when there is an increased number of geriatric population, the prevalence of dementia increases. If you are more than 60, the prevalence of dementia is told to be 1:10. If you are more than 70, it increases to 1:5. And when you are more than 85, it is up to 1:4. So that is the increase of kind of newer cases or incidents of dementia with respect to age. Now, if you look at a normal cognitive functioning, you can see that in aging, there is some kind of memory loss. It's not that there is no absolute memory loss with normal aging, but there is some age-associated memory loss. But if you identify preclinical dementia, you can actually modify this downward trajectory to a better plateau form. So that is where it is more important. And we have biomarkers for this. So these biomarkers are blood-based biomarkers. It can be imaging-based biomarkers. It can be clinical biomarkers. So biomarker is anything which can help in identifying that whether you are vulnerable and when you can go on to develop dementia. So these are some important aspects. I would be dealing more with the imaging biomarkers because that is where the expertise of a mathematician actually is required. So these are some of the clinical studies on aging. We focus at our center, we focus on assessments, we do blood biochemistry, we do imaging obviously, we do studies for primary, secondary, tertiary prevention. Primordial prevention means reduction of risk factors. If you are at risk for developing hypertension or diabetes, you are pre-diabetic, you try to give advice so that the pre-diabetes can be reduced. And there are also brain banks, genetics, autopsy, and histopathology studies. These are the other extreme of kind of research that we do. So these are some of the landmark studies. I will not go into detail, but these are some things which are quite important to understand. For example, we all know that blood cholesterol is bad, and that people who have cholesterol can develop heart attack. How do we know this? This knowledge came from the Framingham Heart Study. We know that smoking is bad. You can develop a stroke or you can develop pulmonary problems or cancer. How do we know this? Global Burden of Disease and None study. Health and Retirement study and other worldwide longitudinal studies have given an insight. So for these kind of neurodegenerative illnesses, correlation doesn't mean causation. And to identify causation, you should identify the people serially across time points. And that's where time series data is quite important, especially in identifying and early detection of neurodegenerative disorders. So at CBR, the Center for Brain Research at the Indian Institute of Science, what we do is we have two senior cohorts. One is an urban cohort known as the Tata Longitudinal Study of Aging, which I am a part of. And then there is a rural cohort at a place called Kolar. You would have heard about Kolar. In Kolar district, there is a taluka known as Srinivaspura. So at the Srinivaspura taluka, we have a rural cohort which constitutes about 10,000 individuals. And urban cohort constitutes about 1,000 individuals who are elderly. And we follow them up serially with all the assessments. So these are the kind of assessments that we do. So I represent this part now. And from Bangalore, we have the urban study, and rural study, we have the SANSCOC study. And we do a detailed assessment wherein we collect all the data sets. Now, coming to dementia. I'm sure most of the audience would know what is dementia. Everybody is well knowledgeable about this particular aspect. But dementia means that you will have memory problems along with issues with thinking, perception, reasoning, judgment, attention, language, and other cognitive domains. So just because you are having a small memory problem doesn't mean that you have dementia. But just because you don't have any other issue also doesn't protect you fully from dementia. The reason is to identify the type of memory problem. If the memory problem is very severe and it is affecting your functioning, then it is severe enough to be evaluated in detail. And that's where it's important. And there are different types of dementia. The most common types of dementia are Alzheimer's dementia, which is seen in majority of the people, about 55 to 65%. The other constitutes the vascular dementia, Lewy body dementia. Vascular is due to stroke, small strokes as well as large strokes. Lewy body dementia, frontotemporal dementia, and other types of smaller dementias like Huntington's, mixed dementia, and so on. Now, this is the main aspect. We have to do neuroimaging. Now, neuroimaging is an important tool. We have the CT imaging. I'm sure many of you would know what is the CT. It is like X-ray, which actually takes cross-sectional cuts of the brain, and based on the intensity, actually based on the density by what is known as Hounsfield's unit, and we get the CT images. But most importantly, CT is, because it's X-rays, it can also be an invasive form. So if you are exposed to CT scan, you can also develop the increased risk for developing cancers and other problems. But in emergency situations, CT scan has to be done. But in dementia, where you have to serially evaluate, CT scans are not preferred. Instead, we prefer what is known as the MR imaging or MR scanner. So this is the state-of-art technology which is being used every day, and you have heard about MRI systems. So what happens in a normal MRI? In the middle, you can see the structural MRI images. So you can actually see this is the brain in a person who is normally aging. Versus somebody with dementia, you can actually see the brain is smaller in size. The black areas are becoming bigger, which are the ventricles. And somebody with frontotemporal dementia, the anterior part or the frontal part is becoming more affected. It's very difficult for an expert clinician also to make it out. So that's where AI and ML can actually help in identifying these things. And that is the place where actually, if you can look at topological kind of analysis, it could help us in identification of dementia and prediction also in a large cohort of people. So that is very important. So this is something known as PET scan. I'm sure you would have heard of PET also. PET scan is done in cancers, especially in India. However, PET scan is also useful for identification of dementia. The reason why PET scan cannot be done again is because it is invasive. It's a radioactive chemical which is being used. So you cannot use it much. So these are different types of PET, amyloid PET and tau PET. Currently not available in India, but very soon it would be there. So coming to neuroimaging in dementia. So if I were to tell you that all the three of them suffer from what is known as Alzheimer's dementia, but you look at the brain pattern, the brain atrophy pattern is completely different across the three of the groups, three of the patients. So patient A, patient B, and patient C, all three have Alzheimer's dementia, but three different types of Alzheimer's dementia. If you look at, this is the hippocampus, wherein the short-term memory is there. And if you look at this person, the parietal lobe is kind of eaten up. You cannot see anything. And here you can see the lateral parietal and the lateral posterior temporal lobes are eaten up. So this is known as logopenia. But I want to just give you a challenge to tell that it is not as easy as it sounds. All the three people have dementia. All the three people have Alzheimer's dementia, but they have different patterns of atrophy or different patterns of changes in their brain scans. So how do we go about it? That is where the challenge lies. So in neuroimaging, the generalized kind of consensus is, first you do a detailed assessment, clinical and neuropsychological evaluation. Then you do a structural imaging. And along with structural imaging, if you feel that it is more like an Alzheimer's dementia, you can go for a PET scanning or CSF studies. Now, anything below this level is not available in India at this point of time, except for PET, and A-beta PET is not available. So we have to do what is known as FDG PET. FDG PET also is not a definitive diagnosis. So there is no clarity. We have to do the CSF study. CSF study, you would have heard, they will actually put a needle in your spine and take some amount of fluid, which is known as the cerebrospinal fluid, and you can analyze that for some chemical biomarkers. And then this pathway 3 is when there is motor problems also, like Parkinson's disease. For example, somebody with tremors or movement issues, slowness, and all that, they can also get the SPECT scan done. So these are different ways how neuroimaging is done at this point of time in our country. And these are different images that we get. So if you can see at the bottom, the clinical utility keeps on reducing, whereas the research utility keeps on increasing. And we are somewhere at this point. We have not gone beyond this. So beta amyloid PET is not available in India. Tau PET is not available in India. It will very soon come. The other two studies are at this point of time not available. but these two, the structural MRI and FDG PET are available. So it is at this point of time, we have to start initiating some kind of analysis to understand what differentiates the controls or the healthy older adults from those with dementia and those with pre-dementia also. So that is where our studies should actually focus on. So neuroimaging analysis is itself a big area. It requires to be kind of looked into at different domains. You have to look at maybe a voxel-based kind of morphometric analysis. Maybe you have to look at a segmentation-based analysis. Maybe you have to look at visual rating scales. So all that aspects. But I would try to say that if you were to look at and train data sets, especially in large samples, what you'll be doing is you will be using deep learning paradigms. So DL paradigms mainly for MR images. Then I would try to tell something about the shape of data and how the shape of data could help in kind of analytic aspects. And I would give an example based on a study which all of you can, if time permits later, can go on and refer to. So this is the structural imaging, and you can actually see the anatomical parcellation and the functional parcellation because both are different. fMRI, I told you, is a task-based fMRI or a kind of resting state fMRI, which depends on the bold signal. Whereas the structural MRI actually depends on what is of different sequences on the activation of protons. And these protons, we have in our body a lot of water molecules, and these are activated by this particular imaging sequences. Like we have T1 sequence, T2 sequence, diffusion weighted, and so on. There are many sequences. I don't have to elaborate that. But just to get a glimpse of it, we may have to use DL paradigms for MR images. And that is the aspect which can be useful for this particular audience. So where has been DL been quite successful? That is what is being commonly used. Because you have enough data where you can actually train the model will learn, and then you can give a prediction. For example, this is with respect to a tumor pattern. You can see a tumor in this right side. So actually in MRI, this side is the right and this side is the left. Patient is lying down and you are seeing the patient from the foot end. So this should be his right side and this should be his left side. So if you actually see in such a situation, it's the DL learning has got immense success. The reason for success is that it is predominantly data driven. If you have solid data, if you have a very good number of n number of scans, and you're kind of training your model on these scans by DL approaches, it is very sure that you will get a better predictive value. Now there are unknown patterns which can be also mined. For example, you have 1 lakh individuals, 1 lakh patients, and you have 10 lakh normal people. You have all their scans. You can actually put it together. And you can actually kind of develop a model which can actually predict even a small subtle change. So that is the amount of information you can actually utilize. No pre-processing is required, except for the image size should be uniform. And no histogram, contrast, brightness adjustment are required. So these are some advantages for a deep learning kind of system. Now, there are some scenarios where it is not easy to build analytical models. Can you tell some scenarios where it's not easy? So there can be situations where there could be motion artifacts. It is not very easy to lie down straight actually. If you have experience going to an MRI or a CT scan and the doctor or even to a doctor and doctor will ask you to lie down straight, you will move a bit. And inside a closed system or a closed gantry, you tend to move more. So these are the motion corrupted artifacts. And you may have to correct for the motion correction, motion artifact data or the further image can be used for further analysis. So that is another important aspect. Especially, what about children? We are telling about older people. The children will not lie down still inside the MRI. At that point of time, you may have to resort to give some sedation or you have to give some general anesthesia, which can affect the image at that point of time also. So you cannot do that. Geriatric patients. And in some disorders like Parkinson's, where you always have some movement problem, you cannot lie still in the MRI system. All this can also pose challenges in getting the proper database. And when the data quality QC is compromised, then the training of the SysDL training can also get affected. So that is something which is an important challenge. The other challenges are the lack of large annotated data sets for several conditions. For example, these are some data sets which are available. This particular data set is for tumor segmentation. And this one is for ADNI, which is the Alzheimer's Dementia Neuroimaging Initiative. So this is maybe 10,000s of MRI images, but they all have this kind of issues. But these are for European brains especially, and not for Indian brains. So something indigenous to our country also there is a problem to identify. There are other deep learning challenges. What are they? One is there can be differences in data capture. I get a scan in another scanner and another person gets in a different scanner. Now these are two different companies. There are two different sequences. The T1 and T2 or the T time for echo as well as time for repeat. The parameters of the scan can also change. And because of two different systems, the resolution can also be different. You would have heard about terms like 1.5 Tesla, 3 Tesla, 7 Tesla and all. So some things maybe in Amrita has 3 Tesla, but a smaller center may have only 1.5 Tesla. So how can you match the data of 1.5 Tesla to 3 Tesla? If it is normal for two of us, the matching will be very intricate because the quality can be very much, or the resolution can be different. So if you train a kind of system, a model on such kind of data sets, it is very unlikely that it will give a proper predictive value. So these are some important aspects. So interscanner brain MRI is something of a challenge. And this is an example for multiple sclerosis, which is a demyelinating disorder. Now, some challenges are in deep learning. So in deep learning, for example, if you look at the fMRI volume time series, the data intensity per instance is quite huge. You look at this data set, you have to have 200 time points with a data value of 150 into 150 into 100 for one trial. So the number of trials is less, or the time series data is less, but with each time point, the amount of data gathered is quite huge. It's against the thumb rule of 10 times of the time data which is required. So when you train a model like this, there can be what is known as overfitting issues. So overfitting issue happens, and when that happens, training model is perfect, but when you test it, it is not at all perfect. So performance during testing is not at all proper, and the data augmentation is also not easy. You simply cannot do data augmentation in such scenarios. And also some challenges are huge models with benefits like generalizability come as big price. It is a cost associated. If you have time series data, how many of you or us can go and get MRI daily? And if so, how much of data is going to be useful? So these are cost intensive aspects also. And it's get doubly harder when dealing with complex data, suppose like the MRK space and all. Then if you actually look at, this is one software which has been recently developed, AutoMap. It's a very costly software, but it does a good thing. It actually kind of consolidates all the trajectories and brings out a proper DL model out, which is more predictive. But the cost is quite huge. So this cannot be utilized in a smaller lab or a low and middle income country setup. Also, the challenges are there can be a lot of false negatives. Areas which are not otherwise normally active can appear to be active when you train these models because of the black box nature of the solution. So all this kind of various neural networks in the routine ML, if you have heard about RNN, CNN fixations, all of this work on classifiers and all of them work retrospectively. So these are some of the important challenges. And you would have seen this particular image. Here we can say with about 53% confidence that this picture is of a panda. But we add some noise to it. Okay, you get some picture. You will automatically tell that this is a gibbon. But is this a gibbon? A normal person can definitely, a clinician will tell, no, this is not a gibbon, this is a panda itself. That means in healthcare, we cannot do this. In healthcare, we cannot label them or wrongly label them or give them false positive names. So that is also an important aspect here. That has to be taken care in deep learning. So it's not robust to adversarial attacks. And we have to understand how we can go ahead. So in all these things, the DL is the main tool. Machine learning, especially with respect to the DL algorithms, are robust. There are robust pipelines. I'm just posing these challenges to explain or explore that we have better options. So these are another aspect is that you can do something known as data synthesis. So medical image synthesis, they are normal brains, but you add a tumor to that. Add a picture of a tumor or add a sequence which contains a tumor and see whether you are getting equivalent results with that of somebody who is having tumor. But data synthesis is not reality and it is much away before it is clinically usable. So these are some challenges. So next we have to see what would be a better way to circumvent this particular challenge of the problems with deep learning methods. Is there a method or are there other methods? And that's where the shape of data comes into picture. And I am sure that this conference and along with previous conferences and this center is kind of working extensively on this, and many of the things which I am telling would be very kind of very basic and would be known to all of you. But I'm thinking the students would benefit, especially if you look at the shape of the data, and that's where topological data analysis actually comes into form. And we will try to look into this particular aspect. So how can we visualize data? All of you are sitting here. If I were to visualize all of the people here as data points, we can visualize them as a data kind of linear arrangement like this, kind of a donut kind of arrangement like this, but the donut is more of a 3D, this is of a 2D kind of scattering, and a 3D kind of a spherical kind of arrangement. This may be a spiral, but people will tell differently. So the problem is we have no clue to which manifold they lie in. Could be one of the easily describable ones like this too, or not. Intend to extract topological features of their shape. But the important aspect is that if you try to extract the topological features of MRI images, it will give us a big clue, especially in Indian populations. Because there is a lot of studies which has been found that Indian brains and European brains are very much different. I'm telling about the structure. The function maybe we will be better, we can argue, or they can also argue they are better. But let us not go into that. That is different. The main aspect is that structural differences are there. Whatever is happening is we are treating our Indian brains based on the data which is obtained from the Western or European brains. One reason also is our brains are on a smaller size because in average, the Indian is also average built is smaller. And there are also some regions of the brain which are differently activated. For example, for all mathematicians here, all your angular gyrus, left angular gyrus would be very much active. Whereas for if there are some musicians here, their right temporoparietal region would be more active. If there are some people who are poets or singers or somebody who talks excessively, his inferior or her inferior frontal gyrus would be active. So there are different areas and these activation patterns are also quite important. So the topological data analysis actually captures the shape of the data. Then the question is, why do we, okay, fine, it captures the shape of data, but why do we want to bother with this? We can actually look at the data samples from specific phenomena, which typically lie in the local manifold, and even though the feature space may be vast. So identifying the shapes will help in identifying pattern, and this pattern recognition can actually help. For instance, the manifold of healthy MR brain scans is different from that of Parkinson's scans. It is like manifold, if you have a doubt what is manifold here, just I will give a very simplistic example that you know that if we have 1,000 photographs of foreigners and Indians, you cannot classify maybe the expression, or you cannot classify whether they are having some problem or anything like that based on face images alone. But you can actually classify which is an Indian face and which is a foreign face. So at least you can do that. And that is where identifying the manifold is quite important. Especially in people with Parkinson's, we know some areas are critically affected. We can know that the basal region of the brain, basal ganglia vitae, that would be affected compared to the other areas. So that is something which can be utilized. Now, this is one study which they have tried to actually look at diabetes, subgrouping diabetes and looking at utility of TDA. And the data samples here are visualized as point clouds with a notion of distance or similarity. So that is very important aspect. You can actually see 3 clusters forming, and in the clusters there are smaller clusters. And this kind of system could help in defining the understanding of these subtypes of, this is again subtypes of diabetes, and they have tried to identify how this, and then further you have to do ML based techniques to identify, okay, the predictive value, that how many of them will have this kind of issues. So these are some important aspects. Yeah. So there are applications in classification, clustering, discovering subgroups. So that is very important in understanding, as well as the interactions between the subgroups. Also, this has been used in different ways. So you can now understand it can not just be used for image analysis. It can be used to look at ECG, it can be used to do an echo, it can be used to look at imaging of the liver, and it can be used even for genetics. So that is the amount of utility this is having. Now this is the shape parameter. Now, which of these, out of these three, which two shapes appear similar? Can any of the students attempt? Out of these three shapes, which two shapes according to you are similar? There is no right or wrong, but we have mathematical way to tell that definitely which would be the correct way, identical or common or similar images. So if any students are there, they can attempt. Which are similar? This is a cube, this is a sphere, this is maybe a donut or a torus. Anybody wants to try? Yeah. So I am sure you know better than me. Very correct answer. It's the first two. Okay. Any reason? What would be the reason if? Yes, correct. Now so you are absolutely right. So it is a geometric similarity. But if you look at the geometric similarity, which is an intuitive, suppose you are all mathematicians, but you take it and give to your brother or sister who is a doctor like me, what will they tell? Which is similar, which is so geometric things are non-intuitive. That what you are telling is non-intuitive, whereas geometry is an intuitive. Na? So I will look at the similarity and I will tell, no, you are wrong, this two is same. This looks like Udinoda, this looks like Paripoda, maybe. Okay. So these kind of things, but you know that cube and sphere are similar. And topology considers two objects the same if you can deform one into the other. Now, without tearing or cutting, only bending, stretching, and squeezing is allowed. So there should be a continuity. Like that is the isomorphic kind of thing they were telling. So you can actually see this kind of ball, as well as this can be made into a cup. And this particular mug can be made into a donut kind of shape. So this is what it is. So similarities, definitely cube and sphere are similar, and we can actually look into it by what is the aspect known as the Betti number counts, isn't it? So I think you would have heard about this. And we can look at the beta 0 or the B naught, beta 1 as well beta 2. These are the connected components, the tunnels and voids. And when we actually try to look at this images, if it's a point, the beta naught value is 1. If it's a cube, the beta naught and beta 2, that's a void is also there. And similar with the sphere, but not with the torus. So this is an important aspect which can be utilized. And this Betti numbers can actually be utilized to understand and classify images. And this would be useful, especially in MRI images. So homology, persistent homology is one important aspect of topological data analysis. And homology, as the term implies, is to have same structure. We can compute topological features, mainly Betti descriptors, at different spatial scales. So that is where this kind of data or this kind of analysis on MRI data would be quite useful. And if they are persistent over a wide range of spatial scales, they are known as true descriptors. And if they are true descriptors, it would be helpful to be identified that they are actually there and they are not so kind of artifacts or noise. So this is also very important. So suppose you have multiple points, how do we create a shape descriptor? I think I'll just go through this because almost all the students here would be familiar with this. You have point, which is kind of a simplex, 0D simplex. Then you have 1D simplex when there are edges also. And when there are triangular faces, they are known as the 2D simplex. But their tetrahedrons are called as 3D simplex. So you can actually see 4 edges, and that is where it is. So these are basic building blocks. And I'm sure that the students would also know this. So given a set of points, we can cover the space they plan by building what is known as simplices. And this is one simplicial complex. And actually, a simplicial complex is defined as a set which is composed of points, line segments, and triangles, as well as their higher dimensional counterparts. So you can see this. You build, there are points, you build bolts around these points. Later, you increase the radius, the bolts started intersecting, and then you draw the line segment. So you can actually create a pattern. And when you create a pattern, more bolts are now intersecting, and you can actually kind of understand that if a ball of 4 points intersect, then we can join these 4 points to get what is known as tetrahedron, which is a 3D simplex skeleton. And this is kind of the analysis which would be quite useful, especially when you do MRI data. And if you see that this first one is a subset of the other, being a subset of the others. So inductively, it would help build higher order simplices from lower dimensional simplices. So you have a smaller data difference between normal as well as Parkinson brain, or normal as well as Alzheimer brain. You actually utilize this kind of methodology and develop bigger, higher level of simplices or higher dimensions to actually kind of help in differentiation. So that is where it would help a lot, especially with respect to human data analysis. Now, I have already told about this, that the dth by dth number counts the number of d-dimensional holes, and it can be used to distinguish between spaces. So especially holes is very important. When I'm telling about the holes aspect or the voids beta 2 value is because in brain, what happens if there is dementia, there can be the cells are damaged, and it can actually, there can be shape changes, and there can be minor small holes which can develop. People will tell that there is a stroke and there is a clot there. You would have heard people tell after CT scan, doctor told there's a clot in the brain. The clot represents a hole in that particular region, and you can actually identify. And if you have larger number of data sets, you can predict, okay, smaller holes, more likely that he may develop a bigger hole later. And these aspects can be utilized in this kind of DL-based work subsequently. So Betty descriptor, we have gone through it. So the descriptor stays at 1 for majority of the cases. So that is one important aspect. So the shape of the data cloud represented at Betty descriptor 1 is a shape with a single 1D hole. So that is very important. So if you look at this particular curve, this is a very important graph. I'm sure many of you would have seen this persistence plot. And this is actually, you see this red dot. And it represents the tuple, that is scale of creation and scale of destruction. So this is something very important. And we can actually utilize this kind of data from persistence plots across the images to find out and look at algorithms which can identify and differentiate between a normal brain as well as an abnormal brain. So that is where if you look across the scales, you can actually see this. And you can see that most of the data points should lie away from the diagonal. The points far away from the diagonal are the most important because they are not kind of destroyed immediately and they are persisting. So that is one important aspect to be looked at. I'm not going to much detail, but you should always know that this is only the tip of the iceberg. Subsequently, you have to do further analysis. Further analysis, definitely, experts in mathematics should look at clustering, bag of words, kernel theory on persistence plots, and then you have to transform them into higher dimensional spaces. Then only you can actually look at the differences in detail. So these are some advantages with respect to using kind of persistent homology that is robust to perturbations. Unlike DL, doesn't require huge training data, doesn't need data augmentation. It's not much prone to adversarial attacks, and the results are interpretable. So these are some important aspects. And you can also kind of take it to a higher level by persistence plot to Betty curves. And you can actually make this kind of Betty curve, which is a function mapping a persistence diagram to an integer-based curve. So that is something which is quite important. So from a point cloud, using persistent homology, you can get persistent plots, and utilizing machine learning aspects, you can actually bring about a data-driven kind of approach where you can differentiate and predict the likelihood of developing dementia based on imaging. So just kind of giving a very brief touch on example. If you look at normal brain, aging brain, and those with dementia, and what they have done is there is topological changes with aging and Alzheimer's. And what it shows that gray matter, the density is changed, and white matter, there's development of smaller holes. And this is what they have kind of understood. And both aging and AD will result in loss of white matter volumes and thinning of gray matter. So density of gray matter is reduced, as well as thinning and formation of holes can happen. Whereas gray matter breaks down into smaller connected components, and that can be looked into. So if you look at somebody with white matter changes in Alzheimer's dementia, you can look at the kind of pattern here. It shows that there is a rarefaction or thinning. In those without Alzheimer, it is more robust. So prominent large holes are seen in people with white matter changes in patients with Alzheimer's dementia. So this utility is actually to quantify changes in brain connectivity by computing these topological changes. And you can distinguish between signatures of AD from aging. So what I would like to tell is this doesn't work in isolation. You have to look at the structural image, you have to look at the functional image, and if you kind of correlate both, you can get the better data. But for all practical purposes, structural imaging is much superior. And the conclusion, I would just like to kind of briefly kind of conclude by telling that the persistent homology seems promising, especially for MRI image analysis. And I would be happy if many of you would also try to explore this. And it can be easily extended to fMRI. The reason is because they can be interpreted in graph. So graph theory can be brought in, and you can actually bring in the dynamic kind of aspects which were discussed before. And interpretable results. That is what healthcare wants. You have to be predictive enough to tell that this particular person may develop dementia, and if so, he may develop in next 10 years or 15 years or so. And there is no data augmentation which is required. You don't require larger data sets. You don't have to rely on European brain data sets or anything like that. There's robust to variations and other signal noise ratios. And these are some important aspects. So I'm not restricting only to MR images, but you can actually look at clinical assessments. Height, weight, BP, all these are data points which you can utilize. You can use neuropsychological evaluation data. You can look at blood data. You can look at genetics and epigenetic studies. So the kind of applications for this particular kind of analysis based on persistent homologies, enough and more, and you can actually utilize. So CBR works on all these areas. I will not go into details. This is some of our publications and some of our work. And my lab is especially interested in looking at neurointerventions. So we look at transcranial direct and magnetic stimulation. We look at gait as a signature. We look at the eye scan, which I told you. And we also look at imaging in detail. So these are some aspects which we do. And what is the future of brain research? So you subscribe to GPT-4, ChatGPT-4. And I actually typed it today morning. As a brain researcher or as a mathematician, how can you contribute and what is the future of mathematics in brain research? And I understood that what they have written is, as a brain researcher, you are on frontiers of a cosmic journey. The future of brain research is like a boundless odyssey into the mind's galaxy. And each neuron is a star waiting to be explored. So keep sailing. So with this, I would like to conclude. I thank all the organizers here for inviting, especially Vinod Kumar sir, and I'm happy to take any questions. But I would also like to tell that utilizing AI/ML for image analysis and large language models would be something which is going to happen very soon, especially with respect to research in brain sciences. And this is a study where I'm involved in for fMRI analysis. And if any of you are interested, you can contact me. We are also looking at developing utility of fMRI and ASL sequence to identify whether a person can get into mild cognitive impairment or pre-dementia much before. So if any of you are interested, we have some openings there also. So with this, I would like to conclude. Thank you very much. And this is the logo or the slogan of the Alzheimer's Society, that is never too early, never too late. Thank you very much.
Now, it is the time for asking questions. If anybody wants any clarifications or comments, you can put now.
Sure.
you said you were going to say something about the time series aspect. But what I find is that all these data are taken from different individuals.
Yes.
So they don't represent a time series. So if you have to generate a time series, you must focus on one individual. And you must study what happens to the pattern in course of time.
Right.
That is one thing. Second thing is, I am amazed to see that the topology is different for different stages of this disorder. And that topology disorder, topology change may be happening in a regular fashion because number of holes, etc.
Yeah.
The dynamics is something known about the dynamics behind these pattern changes. So that is number two. The third is a comment. The holes represent the loss of neurons, isn't it?
Yes.
Yeah. So these three.
Yeah.
doubts.
Very valid comments, sir. Thank you for your excellent questions and comments. I think it's very clear because time series data is definitely based on a single person across time. That is true. But with single person also, we can actually extrapolate it if it is the person from the same family. Because in neurological illnesses, many of the illnesses also have a family history. So you can utilize that. That is one positive way to look at it. Now, the second aspect is also in this kind of cohort studies, that's what we are doing. We are doing serial MRIs every year. And every year MRIs will give us a very good way. And so these are people who are 45 years and above who are recruited for our study. And we are doing MRI every year, at least for 20 years. So 45 to 65, we have about 21 MRIs. And these MRIs can actually be looked at in detail, all the sequences. So that is where we are trying to build in, and this cannot be done by a radiologist or by a neurologist single-handed. We have to rely on these kind of approaches, and this would help us. A data kind of deep learning kind of approach would help in predicting that the person or the particular people who are vulnerable may go on to develop dementia. So dementia is just one disease I'm telling, but there are many other diseases which we can actually look into it. Yes, sir.
Thank you.
So yes. So it is, yes. We have to match with the age also. But usually what happens is usually the dementia, the atrophy, usually for a normal person, the atrophy usually sets in after he is 65 or 70. The 45 to 65 is the window period. That is time when we have to actually look into detail. And especially in the menopausal females, ladies who are undergoing menopause, there are also significant brain changes comes. So that is some study which is actually being done. And we have identified that post-menopausal, the cognitive dulling is there. Even though it is not fully evident, there are some areas there are impairment. Yes, sir.
Okay. Anybody else?
In recent days, some ads of the hospitals, it is saying that a deep brain stimulation. Is it possible actually?
Yes. Deep brain stimulation is done. It is FDA approved for intractable Parkinson's, severe Parkinson's, wherein you insert an electrode into a basal ganglia region called the globus pallidus interna or subthalamic nucleus. You stimulate the brain, and the tremors will reduce. Okay, but it is only for tremors. It won't improve your cognition. It will not improve memory. There are people telling many things on stimulation. They will tell about many things, but it's not evidence-based. DBS is evidence-based, only it will reduce the movement. It will not improve your memory. There are also a lot of research which actually tells that DBS can cause newer psychiatric problems also. So that is one challenge.
One more question, sir. Will dementia cause to this impairment of cognitive thinking?
Yes.
Yes. And the medicines for, that is medication for that, any side effect or something like, will the chances of cardiac arrest will increase or something like that?
Yeah, not cardiac arrest, but any medicine you take will have its own side effects.
Yeah.
Okay. Even though people tell Ayurvedic medicine doesn't have side effect.
From my experience that I'm asking.
Every medicine will have side effect. Even if you take a paracetamol, it will also cause its own side effect. Now, dementia, the current medications focus on improving the neurotransmitter level. So they give what is known as donepezil or galantamine, rivastigmine, like that. The side effects of this medicine are not very significant. Mainly it is gastric side effects. Otherwise, some of them will have some reduction in the heartbeat. That is, if it is 90 pulses per minute, after taking the medicine, it will become 70 or 80. If it is below 50, you are supposed to stop the medicine.
Okay. Right. Thank you, sir.
Sure, sir.
Are these topology changes reversible? Seems like that.
So I would feel that the early topological changes would be reversible. That, yes, early. I am not, by early I mean that there is something known as white matter changes.
Any experiments?
There are a lot of studies. So anything due to vascular risk factors. For example, you have a mild stroke. Okay, you go to a doctor, you will have a change in the MRI. After 2 years, you are fully controlled for your sugar, diabetes, hypertension, everything. And then after 2 years, 3 years, you go, that particular hole may not be there at all. That is where neuroplasticity comes into play.
Transmitters, neurotransmitters.
Yes, neurotransmitters.
They have a role, isn't it?
They definitely have a role. Yes, 100%. So neuroplasticity, I mean, is not just functional plasticity, but structural plasticity also. That is, there was a concept that neurons don't divide. That is why brain tumor is not neuron tumor. Brain tumor is actually a collection of cells of the non-neuronal cells. But now what has been identified is with memory. So I am talking to you, I am learning something. Even small dendrites in my neurons, there are structural changes which is happening. So the structural changes are actually formation of what is known as dendritic spines. These are at nanometer level. But when I'm not using my knowledge, or when I'm not using it regularly, that dendritic spine will shrink off. So at some level, so age is definitely an important variable here, or a main mediator. But at some level, 45, 50, middle ages, neuroplasticity can definitely help.
Population changes.
Yes, exactly.
That affects the neuroplasticity.
Plasticity. Yes.
So is it true that dementia can be diagnosed if we look at only the ventricular region and hippocampus?
No. These are very important regions. Hippocampus definitely specific for Alzheimer's dementia. Ventricles, what is known as ventricles can be, size can be changed due to many reasons. If you have an infection, you would have seen small children with very big heads, which is known as hydrocephalus. That could be due to an obstruction in the flow of the ventricular system or the CSF flow, which will make the ventricles big. If all of us subject ourselves to MRI, all of us will have different ventricular size. That can be congenital also. But what happens after a particular age, hippocampal is definitely an important aspect. Along with hippocampus, if you look at other brain regions, which is amygdala. Amygdala is important for fear, emotion regulation. So that also gets affected. If you see elderly people, means we are all going to get elderly hopefully, but if you see elderly, they are more emotional compared to how they were when they're in their middle ages or young. So there is an amygdala changes which is also happening. So these have to be looked into.
Thank you.
Any other comment or doubts?
Yes, sir. Yeah. So actually, if you want to prevent dementia, people are telling you have to prevent it when you are a fetus itself. So that is the truth. If you look at neuropsychiatric illness, the markers of any neuropsychiatric illness doesn't start in your puberty or in your middle life or after marriage only. My wife got angry, that is why I became psychiatrist. No. It is because you are vulnerable from your fetal stage. Okay. There's a big element of genetics, but everything is not genetic. So that's why the epigenetic concept is there. So even if you have a genetic vulnerability, if you are brought up in a situation where there is a lot of support and you are also able to improve, so neuroplastic changes will come. And there are people in the family, 5 of them have developed dementia, 2 of them did not develop dementia. That reason is because the other 5 were smoking, other 5 were into other problems. They were having much depression, anxiety, and all that. Depression by itself, or sleep deprivation, alcohol, substance use, all are independent risk factors for developing dementia. Whereas if you live a very sattvic or a very proper lifestyle, it has been found that that is best way to actually reduce the incidence of cognitive impairment. So there are a lot of studies on this actually, very interesting area. There are. So, yeah. It is all statistical, definitely. But our aim is actually, if you are supposed to vulnerable and you are genetic risk, and you are likely to develop dementia by 50, if you can utilize some strategies to actually prolong it by another 10 years, that would be beneficial. So it is both. If it is late onset depression, that is depression after 50 years of age, it is a likely risk factor for developing dementia. But people with dementia are more likely to develop depression. Physically means I'm not. Yeah. So physically also it can affect the brain cells, or example hippocampus. So we have some publications to show, actually there are previous publications also, and we have repeated it in India, and we have found that people who are at risk for developing depression or who have developed late depression, they tend to have smaller hippocampal volumes. They also have ApoE4 gene. If you have ApoE4 genotype, you are more likely to develop depression and dementia. So there are a lot of studies, but depression is as a late onset depression is an independent risk factor. So that doesn't mean that it should be clinical depression. Depression doesn't mean that I am feeling low is depression. There should be clinical depression, then only it is likely to do. Yeah. Yes.
Any more? Brain is a fractal, right?
Yes.
Is it a fractal, right?
Yes.
So have you tried your research in the fractal point of view and explain dementia there?
We have to do that. That is more of a dynamic. Yes, we have, because
Yeah.
we have to do that. That's a very important area to be done. But this is a very small beginning. It's not very easy. If you try to look at brain at odd level, there should be another 500 people like me doing on this thing, because there are enough and more things to look at it. But fully agree, sir. I think that's an area we have to look at. Yes.
So with this, we thank our speaker for his excellent presentation.
Thank you.
Thank you for the enlightening session, sir. May I request Dr. Sunny Kuriakos to hand over the memento to Dr. Thomas Krieger.
Virula.
Thank you, Dr. Sunny Kuriakos, for chairing the session. Next talk is an invited talk in 2 parallel sessions. A talk by Professor Saptarshi Bej
which is actually greater than 2. And by doing a parameter optimization, you have to find that what is the appropriate k in your case, right? So this algorithm was called the Loras algorithm, and this is how, for example, the synthetic data distribution looks in case of the SMOT algorithm. Here you can see the blue points is the minority class and the red points are the majority class, and you can see that there is a lot of intersection between the minority and the majority class. This is also another improvement on the SMOT algorithm, which is called the borderline SMOT algorithm. Here you see that this overlap somewhat decreases, right? Here also in the Adasin algorithm also, here it doesn't really seem to decrease. But for Loras, here you see that in some regions, for example, in the outlier region or this region, where there is much more data points in this kind of algorithms, for Loras in this region or this kind of regions, you do not see that spread of the data into the red class, right, in the majority class. That means that in this way you can actually control the spread of the data and control the minority class synthetic data manifold to interfere with the majority class manifold, right? So we actually also tested the performance of this algorithm on quite a few data sets, and so these data sets were chosen from different domains, and they are diverse in terms of the imbalance ratio that they have, which means the ratio of the minority to the majority class, and also the dimensionality and absolute imbalance and these kind of things. Absolute imbalance means that the minority class, there is a minority class and it is actually very, very small. So in the sense that, let's say you have less than 50 data points in your minority class, irrespective of what is the imbalance in the majority class. So for small data sets also we have tested this. So in this case we have observed that, so by the way, in case of imbalanced data sets, evaluation is not that easy, because in this case accuracy doesn't work. Why? Because let's say I have 100 patients, and I have 100 data points. Out of them, 90 are healthy individuals and 10 are patients, right? So if my prediction model can detect all 90 healthy individuals properly, and detects and cannot detect all the patients, then my confusion matrix sort of looks like this. If it is a correct detection, then it will look somewhat like this, which means that the accuracy is 100%. But in this case, so the diagonal elements actually define that which are the how many correct decisions are there in each class. So in this case, for the healthy individuals, all 90 are detected correctly. But in this case, for the diseased individuals, all 10 are detected wrongly. None of them are detected correctly. But if you calculate the accuracy, which means the proportion of correct decisions, that still in this case becomes 90 divided by 100 into 100, which means that it will be 90%, right? So if you judge the classifier performance for imbalanced data sets with accuracy, that means that it will give you improper results, right? So there are other measures, for example, precision, recall, F1 score, balanced accuracy, and all these things, which actually can help you judge the performance of this kind of models. So here we use balanced accuracy and F1 score, because F1 score gives you a good idea of how good the minority classification is, and balanced accuracy gives you a good idea how the overall classification is. So here we see that in case, so the slash is actually, so this is written in this format, A/B. A is the balanced accuracy and B is the F1 score. So in this case, in the baseline, when we do not use any oversampling algorithm, we see that the balanced accuracy is 0.553 average, and the F1 score average is 0.325, right? For the SMOT algorithm, we see that this improves. It becomes 0.785, and the F1 score becomes 0.372. So there is an improvement in this case. But in any other, if you look at the other algorithms like MOT2LD, DB SMOT, Cure SMOT, these are all extensions of the SMOT algorithm. I said that there are about 80 extensions of the SMOT algorithm. If you look at them, for all of them, you will see that it either improves on the balanced accuracy or improves on the F1 score, but not both, right? So it can improve maybe the minority classification, but that compromises on the majority classification, and vice versa. But if you look at the LoRa's algorithm, then you can see that it can improve on both aspects. That means on a balance, the LoRa's algorithm works better than the previous extensions of SMOT algorithm. However, we noticed another problem of the LoRa's algorithm, which actually led us to investigate that or drag that research further. What we noticed that there is this paper by Georgi Kovacs, and in this paper, he compared about 80 of the extensions of the SMOT algorithm. So basically, it's a very extensive paper. It actually takes all these algorithms and uses different classifiers like k-nearest neighbors, SVM, decision trees, and all these classifiers are compared that how all these algorithms perform. And for example, with SVM classifier, you see that these are the top 8 algorithms: DB SMOT, polynomial fit SMOT, supervised SMOT, and so on, right? And for the decision tree classifier, and these are the top 8 algorithms, which are ProSyn, Lee, then SMO, BD, and this kind of algorithms. Polynomial fit SMOT is also there, but in this case for SVM it is in the second, and in this case it is in the fourth position, right? So what we see that this oversampling strategies, so these are all oversampling strategies for generating synthetic data generation. But after you do the synthetic data generation, you have to use a classification algorithm to do the classification, right? So the classification algorithms are SVM and decision trees, and these are the synthetic data generation algorithms. But what we see that the synthetic data generation strategies are sort of influencing the performance of the classifier. What I mean is that, let's say DB SMOT is working very well in association with the SVM classifier, does not mean that with the decision tree classifier also it will work very well, right? So if you are doing a benchmarking study, let's say if you are wanting, you have a data set and you want to find that which oversampling algorithm, if you have an imbalanced data set and you want to find that which algorithm, which oversampling strategy you would adopt, and which algorithm plus combined with which oversampling strategy will work the best in that case or work well in that case, then you will probably have to do a lot of benchmarking, because you have to test a lot of oversampling algorithms plus a lot of classifiers, and then you have to look at the cross of that set and to find that which combination works the best, right? So that was there for the LoRa's algorithm also. In this kind of a plot, I think you cannot read it most probably. So the plots, what you can see are these matrices. So basically, so it's a heat map kind of a plot. And on this plot, there are on the row and the column, in both the row and the column, there are oversampling algorithms. For example, this is baseline, this is SMOT, this is polynomial fit SMOT, and this is ProSyn algorithm, and at the last it is the LoRa's algorithm. And what is the ijth element? The ijth element actually tells you that out of 14 data sets, in how many data sets the algorithm in the ith row outperforms the algorithm in the jth column, right? So let's say if I look at this row, this is the row for LoRa's, and here it is written 10, and in the column is for the SMOT algorithm. That means that there are total 14 data sets, and in those 14 data sets, the LoRa's algorithm, which is in the row, is outperforming the SMOT algorithm, which is in the column, in 10 data sets. So in 10 out of 14 data sets, the LoRa's algorithm works better. So that this is how you can interpret this plot, right? And visually you can see in the easy way, because you cannot read it actually, visually you can see that if the row is actually darker in color, that means that the algorithm is working better. So in this case, for k nearest neighbors, for example, this row is very dark for the LoRa's. That means the LoRa's algorithm works very well for the k nearest neighbors. But let's say for gradient boosting, it doesn't work so well, right? For random forest, the SMOT algorithm works maybe better, right? So there are these kind of things. So there is an algorithm dependence so there is a classifier dependence that among the oversampling algorithms also, and this makes benchmarking on a Yes, so this makes benchmarking on a given data set quite difficult because there are numerous classifiers and numerous oversampling algorithms, right? So to solve this issue, we actually devised this ProRAS algorithm, and this is the idea was to develop an algorithm which is sort of classifier independence, which actually can reduce your benchmarking effort. So what we saw that in the paper by this by Kovacs, the paper that I just talked about in the previous slide, in that paper, which actually made a comprehensive comparison of all these oversampling algorithms, they also identified the top oversampling algorithms, and these two, the polynomial fits mode and the ProSyn algorithm, these two are the top ones. And we actually adapted some features of this algorithm, the LoRaS algorithm, the ProSyn algorithm, and polynomial fit, which were the top two algorithms from there, to actually devise something called the ProRAS algorithm. And this algorithm actually enables you to, I'm not going into the minor details of the algorithm, but the algorithm has 4 modes. And depending on the choice of these 2 parameters, the algorithm converges in one of these 4 modes. And these 4 modes actually helps it to choose a proper strategy given a classifier. So if you choose, let's say, decision tree, and if you choose, let's say, this mode, you will see that decision tree works better. If you choose, let's say, k nearest neighbor, maybe this mode will not work, but maybe this mode will work. And if you have a given classifier, and if you choose one of these 4 modes, you will see comparatively, if you, depending on the choice, comparatively it can achieve this classifier independence. What it means that it can be compatible with any classifier. So and we also defined a measure of classifier independence, and we, using this measure, we actually did this, and the same kind of plot in this. You see that for the last row, the last algorithm, that is the new algorithm, the ProRAS algorithm, we see that the last row is always dark. By the way, we actually did parameter optimization for all the oversampling algorithms just to ensure that we do a fair comparison. So we actually searched the parameter space of all these algorithms, and for ProRAS also we chose the proper strategy among the four modes that I talked about. And we saw that for the ProRAS algorithm, you can see that the last row is dark for all the 4 cases, for the gradient boosting, random forest, k nearest neighbors, and logistic regression. What it means is that is with proper choice of mode, the ProRAS algorithm works well with every classifier, right, which was not present in the previous algorithms, right. Having said that, in this case also, there are different questions. For example, one is that we still have to do some optimization to actually choose the proper modality, that which mode of oversampling in ProRAS works best with which classifier. So so until now we actually talked all about this. So there is the high variance case and the low variance case. I will not go into too much detail, but the idea is to actually sort of draw somewhere in the middle. To model the convex space such that the synthetic sample generation is somewhere in the middle of the low variance and the high variance case. The low variance case actually, the high variance case actually makes them interfere, and the low variance case actually makes the synthetic samples not do too much help to the classifier. And there is whatever is in the middle, we actually call it convex space learning, which what it means is that to generate the synthetic samples, but this alpha 1 to alpha k, the convex combinations that we are using, we have to learn those in the sense of we have to treat those as parameters, and we have to find the proper values of alpha 1 to alpha k for different data sets, for different neighborhoods in those data sets, and these kind of data spaces. So that is what we call actually convex space learning. And there comes the deep learning approach, which we actually, so these are the two previous papers that we published. And now what we have done is that this convex space generative network, which is a generator discriminator architecture, what it does is that it actually takes a data set, and the generator takes actually neighborhoods of the data set as input, shuffled versions of the neighborhoods of the data set as inputs, and actually it creates convex combinations of those neighborhoods, and the discriminator tries to discriminate that or to classify that against the rest random samples taken from the rest of the data space, right? So it ensures that the training is done in such a way that the the alpha, so basically this alpha 1, alpha 2, alpha 3, these coefficients are what we are learning during the process, and we are ensuring that these are learned in such a way that the synthetic samples are generated within these nonlinear data neighborhoods, right? So this is what this algorithm takes care of. And this was also very recently published in pattern recognition, this algorithm. And we also showed that this algorithm doesn't really outperform LoRa's, the ProRAS algorithm that we talked about before, but it actually performs at par with this algorithm. So this is the architecture of this algorithm. I don't want to go too much into details because of the time constraint, but this has some specialties which I would like to mention. That first of all, this is the first deep learning architecture for generating synthetic data from the convex space, as we talked about. And because these are convex combinations, these actually preserve certain statistical properties. For example, if you calculate the expectation of the synthetic samples, you will see that expectation matches with if you assume that x1 to xk, they are from the same distribution, independent distributions, then you will see that expectation is actually equal to the expectation of the distribution of this x1 to xk. Also, this architecture, this kind of a deep learning architecture, opens up the possibility of a pre-trained neural network if we want to use a pre-trained neural network. And of course, this also in general, outside the context of data imbalance. So until now I have been talking in the context of data imbalance. Outside the context of data imbalance also, it can help us generate synthetic tabular data sets, and that can have several uses. For example, in case of data privacy, so if you cannot share your original data, you can share synthetic data, let's say, and that can help you preserve privacy. So that could be one application. So there are several actually challenges of tabular synthetic data generation. For example, cognitive evaluation is the first one, which means that if you look at image data sets, these are all synthetic images, and you can immediately judge that how good a synthetic image is or isn't. Even if you read at a synthetic text generated by a ChatGPT model, you can read and you can make sense out of it, and you can decide that how good is that or not. But for tabular data set, if you generate synthetic data, you cannot immediately see and tell that whether it is good or realistic or not realistic. You have to go through several kind of analysis. So this cognitive evaluation is not there for tabular modality. And then there is this task specificity. This is also called utility versus privacy. So this is some sort of a dilemma. So suppose you the privacy problem that I talked about. Suppose you want to preserve privacy. That's why you are generating synthetic data. And in that case, if your data is too realistic, then it is problematic. You cannot preserve privacy. But if your data is far from reality, then also it is no good, because you cannot do statistical analysis or further downstream analysis on that kind of data. So there is a balance that has to be struck. There has to be logical and functional dependencies. These have to be preserved in a data set. For example, in your synthetic data, if there is a male person who is shown to be pregnant, then that is absurd, right? So that is logically absurd. That cannot happen in synthetic data. These kind of challenges are not present in other modalities like image or text data. So this is also some kind of challenge. And of course, there are other different kinds of tabular data, for example, longitudinal data and so on, for which also there are not many models. Yeah, with that, I would like to conclude the talk, and thank you. I guess I got a bit late. I had time till 12:15, so I took the liberty. Thank you very much.
Hello.
Thanks, Dr. Saptarshi, for the nice talk. Any questions from the audience? Okay, so I have one question.
Yes.
So, I mean, the strategy you sort of described is about oversampling, right?
Yes.
Can it be turned in inverse way? Like there are problems where you have more data than required. You know,
Yes.
the data is big size is a problem to train the models and things like
Yes.
that. So can we use, you know, reverse these ideas to get a smaller subsample out of the data?
Yes, there are actually several strategies. So basically, I showed one strategy called undersampling also, that is also used. So there is also from very big data, you can actually choose some representative data that can actually represent actually the data space aptly, so that the smaller data can be used for faster calculations, and it will still can be scaled up to the larger data set. Of course, the most obvious way would be to do random undersampling, but there are strategical ways to do this.
That's what my question was. Like, the strategies are they similar to what you described, or is it?
There are several strategies actually. Some strategies will be that which data. So if you want to reduce the data, some are deciding that which data sets, which data points do you want to keep. Some are also deciding which data points you want to delete. So there are mainly these two kinds of approaches. Some actually focus on not exactly with convex space learning, there isn't, but there are other kinds of choices.
Okay, thanks.
Thank you very much.
Okay, thank you, sir. Now I invite the chair to hand over the memento to the speaker, Saptarshri Pitch. Thank you, sir.
Now we will have the invited talk by Dr. Shyamal Ghosh on a bivariate copula for modeling negative dependence application to New York air quality data. The chair of this session is also Dr. Siddharth Preetham, sir. So I request him to please chair the session.
Hi. Welcome to the second part of the third session. So the talk is by Dr. Shyamal Ghosh. He is assistant professor in School of Data Science at, again, Indian Institute of Science Education and Research, Thiruvananthapuram. He has also worked as assistant professor at Indian Institute of Information Technology, Guwahati. He has done his postdoctoral fellowship at University of the Free State. He has served as visiting scientist at Applied Statistics Unit, Indian Statistical Institute, Kolkata. He did his PhD from Indian Institute of Engineering, Science and Technology, Shivpur. The expertise includes statistics and probability, mainly mathematical theory of reliability, dependence modeling, stochastic degradation modeling, statistical inference. He has the credit of 14 publications to his name. Thank you.
Thank you for your introduction. And I also thank Professor Vinod Kumar for inviting me here. And also to all the basically coordinator who is performing this conference. Yeah, thanks all of you. Okay, so today basically I will talk about modeling of dependence data. Okay, so in reality, you all basically in reality every day we are getting several kind of several type of data, and among this data there are many data we will get where the data basically are dependent. The variables are dependent. Okay. For example, you can think about the rainfall intensity or rainfall rainfall duration. Okay. So the thing is, when there is intense rain, then the duration is bit less. Okay. So there was one study to basically model the flood frequency in a particular area. There they showed that there is a negative dependence basically between the rainfall intensity and rainfall duration. Okay. And also you can think about different kind of data like crude oil price and airline stock. So in airline, the main cost basically for their fuel, and their fuel is coming from this crude oil. Now, if there is increase in crude oil price, then there will be less earning in the basically less profit in the airline. So their stock price will decrease. Okay. So that is also they are kind of dependent, and they are negatively dependent. So if one is increasing, then another one will decrease. And also, for example, if you just study the relationship between the unemployment ratio and inflation, there is also a negative dependence. For example, if the unemployment is very less, okay, then what will happen? Then there will be very few people available who will do some kind of job or something. Then the employers have to pay some more money to the employee so that they can get some person for their job. Then basically their firm has some kind of they will get less profit. So at the end it will go some kind of, so they have to increase their price sometimes. So it caused to this inflation. So they are also kind of negatively dependent. And yeah, also there are some studies based on this effect of temperature and precipitation on vegetation growth or this thing. So there are, in real life actually we will get different kind of data which are negatively dependent. Also obviously there are many things which are positively dependent, and I am mainly considering this negatively dependent data because till now many type of study has done for modeling the positively dependent data, but very few work has been done for this negatively dependent data. Okay, and I will focus on this part only, on how to model this negatively dependent data. Okay, one basically effective tool for modeling this dependence is Copula, that all of you are know probably. Okay, and yeah, Copula is one of the most effective tool, and you can get this application of Copula in almost every field. Okay, and this dependent data is basically mainly you will get in finance and also in engineering and in almost all the fields. If you just for application purpose, you can see this kind of, these are the books by Joe, and these books are very useful and they are giving many application for this dependence modeling using Copula. Okay, now before going into the details, I just want to briefly introduce what is Copula, briefly define what is Copula. Copula actually is a mechanism which allows to isolate the dependent structure in a multivariate distribution. So if a multivariate distribution is given, what Copula did, Copula basically separate the dependent structure from the multivariate distribution. Now so this Copula is basically the structure, how they are dependent. That thing we will model. So what is Copula? Copula is basically a function which is from an d-dimensional unit cube to a basically 0 to 0, 1, and it's a d-dimensional. Okay, a d-dimensional Copula is a joint cumulative distribution function of a d-dimensional random vector on a unit cube with uniform marginals. All of marginals should be uniform, and uniform on 0, 1. That is the thing. Okay, so and obviously since it's an d-dimensional cumulative basically CDF, so it should satisfy these basic properties. It should be non-decreasing. If one of the component is 0, then it should be 0. If all are 1 except 1 is u, then it will be text values u. That are the basic properties of the CDF. Okay, multivariate CDF or d-dimensional CDF. That property should satisfy, because we are saying that Copula is basically a joint cumulative distribution function of a d-dimensional random vector on an unit cube, and only additional condition is there, its marginal should be always uniform. Okay, this is Copula, and this Copula is help us to basically the isolate the dependent structure. That thing we will use. Okay. So in recent time, actually, several study has been done to model the negative dependence data, and in almost all the cases, so dependence mean you can say, for example, you can consider the correlation coefficient. Okay. Now, correlation coefficient theoretically it can take any value between +1 to between -1 to +1, right? But which part we are saying negatively dependent when the correlation coefficient takes value between -1 and 0. Okay, that is the I am saying referring as the negatively dependent. Okay, now several studies has been made in the literature to basically model a distribution function or a copula whose correlation coefficient can take values can take any value between -1 to 0. But all these studies have some limitation. They didn't get any kind of copula or distribution whose correlation can take in the whole range. Okay, so these are some example. So for so for modeling this Kindle-Staff and Fearman's row, that basically use this correlation structure to measure the dependency. And even if you just consider, so several study I have mentioned that several study has been done in the literature, but they all came up with some kind of limitation. For example, it was a long-term study is going on. In 1978, they have basically defined this bivariate distribution. Okay, they showed that its correlation coefficient can take values only till -1/3. Okay, later several generalization has been made. For example, Baimov and Coates and this author, they have introduced 3 and 4 parameter extension of this FGM copula or FGM bivariate distribution, but they are also come up with some limitation. Here they are saying that this negative correlation can goes up to -0.5. Okay, and also in recent times, for example, recently Kure also introduced another bivariate copula. He has also come up with a limitation. His correlation coefficient can goes up to -0.6, not more than that. So this is a big limitation. So our target was to model a bivariate distributions or a copula whose correlation coefficient can take basically values it can take any values between -1 to 0. Because in real life we can get or we will get many data where the dependence is basically taking, for example, -0.75, okay, or maybe -8 or something. But then if that kind of dependency is there, then there is no model which can be used for modeling this data. Okay, so that was our point. Okay, now I am going back before that also. So this Kindle-Staff and Fearman's row, these are the correlation coefficient that basically used to measure the dependency. And not only that, together with some kind of dependence notions is also there, because you will see that you will get two random variable that may be strongly correlated, but their association is very weak. Okay, so there is a difference between, I hope you all know that there is a very small difference between association and correlation. So association is basically what we say. So two variables are associated if in one variable there is some information about the other variable, but in correlation that is different. So the thing is, correlation, if one is kind of increasing, then one is kind of increasing, then either it will increase if it's positive, and if one is decreasing, then another will increase. That is the thing. Okay, that we will refer as negative. Okay, now to measure this association in literature, several notions of dependence was introduced. Okay, this Lehman in 1966 basically he introduced these three notions: quadrant dependent, regression dependent, and likelihood ratio dependence. Apart from that, recently many notions of this negative this dependence was introduced in the literature, and these dependence are basically has application in finance hugely. Okay, because in finance data you will get several data which are either negatively dependent or they are strongly positively dependent. Okay, now to model or to study the association and also the dependency between them, between the data, they use this kind of dependent structure. Okay, now So as I mentioned, so there was no such distributions whose correlation can take between -1 to 0. Together with it should satisfy, that distribution should satisfy all the notions of dependence. And basically I will focus on all the notions of negative dependence. So that is a kind of challenging task. Okay, so that we have tried to basically handle in this work. So what we did, we first introduced a bivariate distribution. Okay, and this is a work with basically I was also involved in this work. This is the work with Professor Projamitra Bhuya and Professor Murari Mitra and Priyanka Majumdar. All we are actually 4 authors were there. Then we have first initially introduced a bivariate distribution whose basically marginals are, one is exponential and another is basically a member of the skew log Laplace family. Okay. Now, if we take this distribution, these marginals, okay, basically these distributions correlation coefficient can take any value between -1 to 0. Okay, that part is done. Now also we have showed that it satisfies almost all the notions of negative dependence. Okay. Now what we did, we use the structure, basically dependent structure of this distribution to define the copula. Now copula is basically, I will describe that is, we will only consider the structure, then we will use the several different marginals, then we will generate infinite number of distributions. Okay, which basically inherit all the properties of the copula. Okay. Yeah, that is basically we utilize the negative dependent structure inherent in this model to formulate our copula. So from here, using this one result by Nelson. So Nelson is basically the pioneer of this research area, or basically pioneer of this copula. He basically introduced all these things, and this book is very good one. This Nelson 2006. Okay, and we have utilized one basically Clark's theorem to deduct the dependent structure from the bivariate distribution, and the structure is this one. Okay, here this theta is called the dependence parameter. Okay, and I will show you that if this dependence parameter is increasing, then this correlation coefficient basically decreasing and it will goes up to -1. Okay, so yeah, now obviously since I am saying, so this is the copula, so it should set, so it should be a, now it's a bivariate copula, so it should be a bivariate distribution. So it should satisfy that properties of the bivariate distribution. That is the basic thing for kind of checking purpose. So we have shown that all these properties of bivariate copula is satisfied. And now these are the figures that shows basically for different dependence parameter how this copula is looks like. Okay, I am not going into details on this. Now next, these two things are important, this survival copula and also this density of the copula. Okay, these concepts are this the survival copula and these densities. Sometimes what happens, sometimes we cannot work with this main structure of copula here. Okay, sometimes we will not get basically the closed form of this thing, then we have to go with the density thing. Okay, and in this work I am not going I have not used this density thing for real life application of this thing, but this structure I have given here. Okay, next thing, how to generate the data. If you, even if you are introducing a copula, then how you will generate the data from the copula. Okay, so that one method can be using the conditional copula. So we have derived the conditional copula, and we have utilized this thing for generating the data. So first we have introduced the conditional copula. We have basically developed the conditional copula of U given V. Then this is the structure that when V is like, when U is lies between this thing, then it is looks like this, and when U is lies between 0 and 1, then when V is lies between 0 to theta by theta plus 1, this is the form of the conditional copula, and when V is lies between this range, it will be the structure. Okay, and it's obvious, not obvious, we have also showed that this is the regression line of U given V, and it shows that it's an decreasing function, linearly decreasing function in this region when v is lies between 0 to theta by theta plus 1, and it's a constant when v is lies between this interval. Okay, and similarly the conditional variance is also an decreasing function and it is bounded by this quantity. Okay, these are kind of interesting information that maybe if someone is using in terms of financial data, that are useful to explain some kind of features there. Okay. Now how to generate, how we can utilize this conditional copula to generate the data. So that is the thing. For example, we are taking two random number. Basically, we are generating, we are simulating this two random number from the uniform distribution. Then utilizing this thing, we can generate the data from our copula using this small algorithm. Okay, and obviously see here when theta is our dependent parameter. If theta is increasing, then I have told you that this our dependent things will increasing, or basically it will goes up to this dependence parameter. This correlation will goes to -1. So as expected, when theta is kind of increasing like 10, then it's like basically it's become closer to the diagonal b equals to -u. Obviously this shows that if one thing is increasing, then other will decrease. Okay, so kind of negatively dependence is obviously shows. Now we have studied some basic properties of copula, like this. We have basically established that this copula is decreasing, or basically this copula is increasing with decreasing with respect to its dependence parameter theta. Second one is this copula is subharmonic, and this copula is absolutely continuous. I am not going into the details and also not going into the details of the interpretation of the thing. I will basically focus on the data analysis part. Okay, and now see, this is another, this is the main thing. So here we have calculated the dependence thing, basically the Spearman rho and Kindle-Stowe. Okay, and see in both the cases it has the closed form formula, and it only depends on the dependent parameter theta. And this both the cases, this is the Spearman rho. This is an decreasing function in theta, and as theta increase, it goes up to -1. So that one part is done. That is basically that it correlation coefficient, or basically the Spearman rho correlation coefficient, Spearman rho can take any value between -1 to 0. That part is done. Okay. Next thing, we have also showed that this Kindle-Stowe formula is this one. This structure is this one, and it is also a decreasing function, and it can goes up to -1. Okay, and this is basically the figure of the Spearman rho. Basically the graph of the Spearman rho and Kindle-Stowe. I have shown that as theta increases, it basically goes to -1. Okay. Now one thing is there, as expected, this Spearman rho should always be less than equals to Kindle-Stowe. That is also holding here. Okay, that is kind of established result that always Spearman rho should be less than Kindle-Stowe. In our case also this holds. Okay, now what I told, that we have to introduce a copula or bivariate distribution that correlation coefficient can take any value between this range. Together with it should satisfy all the notions of dependence. Okay, so I have mentioned initially that three basically Lemon introduced the main three notions of dependence. One is quadrant dependent, regression dependent, and likelihood ratio order dependence. Apart from this, there are in literature there are many notions of dependence. For example, okay, now this notions of dependence is basically available for both the cases, positively dependence or for the negative dependence cases. Now this quadrant dependent, it can be positive quadrant dependent or negative quadrant dependent. Okay, so what is the definition? The intuitive okay, basically the definition is if the joint distributions of okay, if the joint CDF is less than equals to the product of the marginal, then we will say that these two random variables are negatively quadrant dependent. Okay, now similarly many concept of dependence is available in the literature. For example, this y is left tail increasing in x, or maybe X is left tail increasing in Y. This kind of dependence is basically used in financial data analysis. Okay, they are basically give. Okay, so for it can be used for the, you all know basically that financial data are heavy tail distribution, follow heavy tail distribution. Now to observe the dependence there, this tail in basically this left tail increasing or right tail decreasing, these properties are used there. Okay, and we have showed that our copula is satisfy all these kind of notions of negative dependence. Okay, so this is the kind of results. I am not going into the detailed proof. Okay, that we have showed that if X and Y are two random variables with a copula C theta, with our copula C theta that is introduced in this paper, that then X and Y are left tail increasing, it's denoted as Y given X. Okay, and X and Y are left tail increasing, Y given X given Y, and also the right tail decreasing and right tail decreasing Y given X and right tail decreasing X given Y. Okay, and also we have similarly for the other notions that it is stochastically decreasing, that also we have established, and also we have shown that our copula is negatively likelihood ratio dependent. Okay, it satisfies this property also. Now one thing is there, you can order two real variables. Basically, if A and B two real number is given to you, you can order them. Either it will be basically A should be smaller than B, or A should be larger than B, or they will be equal. But if two random variable, if I give in to random quantity, if I give in to you, how you can order them? It's not an easy task. Okay, so for that thing in literature, several method was introduced. Several notions is introduced. For example, several ordering notions is introduced, like stochastically order, or hazard rate order, or likelihood ratio order. Different kind of ordering is there. Okay, so these two authors, Fang and Zhou, and this in this paper, they have also introduced, if there is some kind of dependence into variable, then how can I order them? For example, x1 and x2 is there, they are dependent, and another two variable is also there, which is x3 and x4. Okay, they are also negatively dependent. Now how we can order them, their dependency, whose dependence is higher than the is the dependence between the x3 and x4 is higher than the dependence between x1 and x2? How we can order them? That is basically introduced in this paper, and these dependents are these orderings are called the negatively quadrant dependent order, and also there is other two, negatively regression dependent order and negatively likelihood dependence order. And we have showed that our copula is basically satisfy all these ordering notions, and these are the conditions. If the dependence parameter theta, or if we impose some condition on the dependence parameter, then we will get the ordering results. Okay, now so we have get the dependent structure. Now basically our copula. Now our main advantage is what? That we can basically use different marginal distributions, and we can put into my copula. Then what we can get? We can get a bivariate distribution. Now that bivariate distribution should satisfy all the properties of this copula. So now what is advantage? If in real life, why this copula is important? So if in real life we are getting that two variable x and y, they are dependent, and their correlation is basically, for example, say minus 0.6 actually, minus 0.6. Now how we can model this data? It's difficult. Okay, so there is maybe infinite number of bivariate distribution by which you can model, and also there is, okay, then another main problem is there are very few distribution is the bivariate distributions is there whose correlation can take this minus 0.6 or maybe more than that. For example, if there is dependence close to 0.9, then there is no such distribution, okay, which you can use for modeling that data. Okay, so now the advantage here is our copula can take any values between -1 to 0, So we can use our copula. Now to basically to get the bivariate distribution, what we will do? So for X we will fit a marginal, and for Y also we will fit a data, we will fit a distribution separately. Now we will get these two distribution as marginals, then we will put into the copula. Then we will get the bivariate distribution that will be represent the data. Basically this real life data for modeling purpose, right? That is our target here. So now we have basically shown with some example for bivariate. For example, here we have considered our marginals are Y-bull. Then how this joint distributions look like. Okay. Now one can take also one as X, one as Y-bull, and another can be gamma also. No need to take both are equal. X and Y, these two are marginals. This marginal can be different. Here I am taking one, for example, here this bivariate gamma is given here, but you can also take one as Y-bull and one as gamma. Then you just take these two as marginal, then you just put into the copula, you will get a bivariate distribution. Okay, whose correlation will be basically can take any value and also satisfy all the notions of negative dependence. Now that is basically very useful for modeling this negative dependence. Okay. Now, yeah, that is the another aspect. So even if we are introducing a copula, so somehow we have to say about the estimation methodology, right? So for that, one possible way is one can say that we can use the basically the MLE, maximum likelihood methods, right? But here some disadvantage is there for using this method. For example, even if just go back, so you saw that you will see that. So for example, I am going back to my copula here. Yeah. Yeah. See here, there is dependence on the basically this theta is our dependence parameter. Now this range is basically somehow involved here. So we cannot easily use the MLE maximum likelihood methods. Okay. So for that is one advantage, and another thing is there are the number of parameter is basically high when you will use this MLE. Okay. So this log likelihood function involves plenty of large, basically potentially large number of parameter. So this maximization problem is become difficult. Okay. So that's why this Harijo in this paper in 1997, he introduced another method. It's called the inference function of marginals. Okay. What we did here, first of all, we will feed the marginal distributions, then we will utilize or then we will maximize the bivariate maximum likelihood function. Yeah, this is the thing. IMF estimation method based on the two separate maximum likelihood estimations of the univariate marginal distribution followed by an optimization of the bivariate likelihood function of the dependence parameter. Okay, so what it's saying, first estimate the marginal distributions, then put into the bivariate distributions. Now that bivariate, you will get a bivariate likelihood function. Now maximize it. Okay, but that is also a complicated thing here. So we have just make little bit changes here. What we did, since we know our correlation coefficient, basically this Kindle-Stowe and Spearman-Rowe has closed from, we have used the method of moments. Okay, so to basically estimate the dependent parameter. Okay, so that is kind of very easy task to do. So that's why we have employs this method. So basically we have little bit modified this technique, IMF. Okay, now I am going to this application. So this application is basically from New York metropolitan area. So in this data set, they have collected the air quality, different kind of measurement was there. Air quality, yeah, they collect different aspects of air. Okay, for 150 days. And here we have see that if we just consider these two kind of variables, one variable is basically average wind speed and the mean ozone level. That two are negatively dependent. Okay, even if you just see their correlation coefficient, this Spearman-Rowe and Kindle-Stowe values is minus 0.59 and minus 0.43. Okay, so Okay, now one can say that how you can, okay, the thing is among these two variable you are getting negative dependent. That does not mean that there is basically a potential relation between these two, right? So actually there was different studies available in literature that there is a connection between the wind speed and the ozone, basically the depth or density of the ozone level. Okay, for example, these two papers are there and many more papers are there. One can see these two papers. These are basically very good publications. Okay, so from that data set we have considered 116 observation. Okay, because some missingness was there, so that's why we have considered only 116 observation. And this is the, if we just plot that two variables, this is the basically plot looks like the scatter plot. Obviously it shows there is a negative dependence if one is increasing. For example, if one is increasing, then other variable is basically decreasing. Okay, and obviously that is captured in this Spearman and Kindle-Stowe. Now we have tried to model this fact. Okay, so what we did, yeah, we have used the, okay, another thing, okay, before going to the estimation, basically the modeling part, and another thing, we have also tested, is there any kind of negative dependence is there or not. Okay, so for that thing we have tested, we have basically showed that there is these two data set or these two variables are negatively quadrant dependent. Okay, and for that thing what we have employed a method proposed by Liu and Sujit, basically Liu and Ghosh in 2021, and using this test procedure we have shown that this p-values are this one. So obviously it basically shows you that there is a negative dependence among the data sets, among these two variables. Okay, now for modeling purpose we will use this IFM technique. So for that what we did, we have fit a model for this wind speed. Okay, and we fit a model, basically a marginal, we fit a model for the ozone density. Okay, then for that thing generally, yeah, this is thing in engineering and environmental science, log normal, Y bull and gamma are the most commonly distribution that are used for modeling the wind speed. Okay, and here also we have checked these three distributions, and based on this AIC value we have considered that gamma gives the best fit for this data set for wind speed. And also for modeling the ozone density, this is also kind of established in the literature that this type of distribution used, and based on this AIC information also we are having that gamma distribution gives the best fit. Okay, so for that thing what we did, we just model this wind speed and ozone density using this gamma distribution. Then we will get the parameter of the gamma distribution. For example, for wind speed what we are getting, the parameter value or the shape and scale parameters are 7.17 and 13 for wind speed, and for the ozone density we are getting the parameter these two. Okay, now we are using the method of moment technique to estimate our dependence parameter theta. Okay, so for that thing our Spearman or Kindle-Stowe have the closed form expression, so we have used that thing to estimate our dependence parameter. We are getting this parameter is this one. Okay, so and now if we just feed that model, it looks like this, our bivariate distributions looks like this one. Okay, and also I have not included also it has also basically established in the paper that when the wind speed is basically increasing, then how the basically the ozone density is ordered. That is also we have established. Okay, that is also in one interesting part. I have not included that part here. Yeah, and these are the references that I have put in this work, basically used in this presentation. Yeah, this thing. Thank you.
Thank you, Dr. Shyamal, for the nice talk. Any question from the audience? Okay. So we would like to thank the speaker again. And
Now I request Dr. Siddharth Preetham sir to hand over a memento to Dr. Shyamal Ghosh sir. Thank you, Dr. Siddharth Preetham, to chair the two sessions. Now we will break for lunch. The lunch will be served in the Chavra Hall near to canteen. And the afternoon session will start at 2.
Hello, hello. 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 Can you hear me? It's okay, right? Yeah. I think after lunch. After lunch may not be that many people.
Let us begin the afternoon session. May I invite Professor A. Krishnamurthy to chair the session.
Well, I will straightway introduce the speaker of this session, Dr. Amit Chattopadhyaya. He is an assistant professor at the International Institute of Information Technology in Bangalore. Received his PhD degree in Certified Geometry Computation from Johann Bernoulli Institute of Mathematics and Computer Science at University of Computer Science at the University of Groningen in the Netherlands. After receiving his PhD, he worked as a postdoctoral fellow at the Université Catholique de Leuven in Belgium. His research interests include computational topology and data analysis, certified geometric computations, scientific visualization, optimization on matrix manifolds, and level set method. Well, of course, all these things are something alien to me. So I don't know whether I will be able to comment anything on your talk. Anyway, I'm just handing over the floor to you. Thank you.
Thank you. Thank you for your kind introduction. And thanks, Professor Vinod and the team for your excellent hospitality during this conference and for inviting me for this talk. So today's talk is about topological distances for shapes and data analysis. So, you'll see in this talk that how topological distances actually help over the ordinary distances. What we see, I think, in data analysis and machine learning, distances appear everywhere. So here we see that what's the advantage of using the topological distances over the ordinary distances. So topology, as most of you are familiar, it's a branch of mathematics for systematic study of shapes. And this is also based on the global properties of the shapes, right? So for example, the holes. And in computational topology, we deal with algorithmic problems in computing such topological features. For example, that computing holes of different dimensions in a topological space. And in TDA, what we do, we add topology with the data, which gives us the shape of the data. What we try to understand the shape of the data by adding the topology with the data. So applications of this we have seen in topological clustering of different data sets and in topological machine learning and so on. And this picture you are familiar, in the morning also you have seen this, so I'm not repeating this. So in topology, this coffee mug is topologically equivalent to the donut. So the data in topology could be quite abstract. We require only the data points to be having some kind of neighborhood so that we can define some sort of continuity in the data, right? Here in particular, we'll be discussing about, we'll be seeing the examples of this kind of data, so, but not necessarily this will be the only data set what we can handle in topological data analysis. So the kind of data we'll be seeing today here in this talk is the scalar data or vector data or multi-field data. Multi-field consists of multiple scalar fields, and this is the vector data. That also you have seen quite a lot in dynamical systems, and so this is the hydrogen atom data for which is a scalar field. So in topological data analysis, what we try to do for all the kinds of data what we have, we try to subdivide the domain of the data into simple regions so that we can find some kind of skeleton as a topological skeleton from the data, right? So we subdivide the data domain into simple regions based on their some sort of equivalence relation, and then we subdivide the data and we find some topological skeleton which helps us to understand the data. That's the overall kind of idea in topological data analysis. And we have seen a few standard tools in computational topology. For example, this simplicial homology, where we compute the different kinds of holes of different dimensions to understand the data. So these are the standard topological tools in computational topology. And in Morse theory, what we do, we apply calculus to compute such holes, right? We try to relate the geometry with topology, and by looking at the local properties, local kind of features in the shape, we try to compute the holes. So that's another way to compute the holes using the Morse theory, which will come again in the coming slides. We'll see this again. In persistent homology, there's another tool. It's a kind of most important tool for topological data analysis and topological machine learning. What we study there is the birth and death of the holes, and show the lifespan of the holes of different dimensions, right? So that has been captured in this kind of the barcode or the persistence diagram. And what we'll talk today also on topological skeletons corresponding to the scalar field. We have the skeleton like contour tree or the Reeb graph, and corresponding to the vector field, or we call it the Morse-Mel fields, we'll be having these complexes. What will be kind of abstracting the topology from the vector field data, or a particular special type of vector field data, which are kind of widely used in topological data analysis and in computational topology. These are the tools. We know that how to compute such kind of tools. So in today's talk, we'll be mostly focusing on this kind of questions: how to detect a topological change in a series or a time-varying scalar or multi-field data, right? When we try to detect some kind of topological change in a series of data, so one way you can do it by visualizing this kind of topological skeleton or abstraction for each of the data. Or other way you can do by computing some sort of distances between these consecutive data sets and try to see that try to detect from this distance plot that where exactly some sort of topological changes is happening. For example, this data set is from a multi-field data, which consists of the component scalar fields like proton, neutron, and total density, which is the proton plus neutron, fermium atom data. So the plot is showing some kind of isosurfaces of one of the scalar fields. I have forgotten which one, maybe the proton or the neutron. And goal is to detect this, the point where the nucleus of the fermium atom splits, and we need to detect this exactly. What we'll see that using only one of the scalar field, they cannot find the exact timestamp where this split happens. We need to apply the multiple fields together to detect the exact split where exactly it happens. So the outline of my talk will be like this. So I'll be giving you little motivation of why topological distances, why not the ordinary distances, why they cannot detect such kind of, or instead, I mean, I would be saying that some examples where this will not work, the ordinary distances will not work. Then I'll give you some topological distances, what has been developed almost like 20 years back for the scalar field data, like between two scalar fields, how usually we can find the topological distances. And then I'll give you some motivation of why multi-field topology instead of scalar field topology, because of course, whenever we are involving more scalar fields, so that will be computationally expensive, but with some benefit. And finally, I'll give you some of the recent development towards multi-field topology and the distance between the multi-field topology. Okay, so first example for why topological distances instead of ordinary distances. So here we have taken some simulated data for these two scalar fields. Two scalar fields are like here I considered this two scalar fields consisting of the height and the paraboloid field. Paraboloid means it's just fx2 equal to x square plus y square, that kind of field. And then we perturb that scalar field with different amplitude, and corresponding to that, we just compute the root mean square for each of these data in this box. Okay, so that's the root mean square plot corresponding to the series of data. So, but this is a topological abstraction, which you will see it later, that what exactly we are computing here. What is this topological abstraction, that we'll see. So what you see here from this ordinary distance plot using this root mean square distance, right? So we do not get the where the some kind of topological change is happening, whereas if we plot the distance, some sort of distance which will be defined later, if we plot the consecutive distances between this, so we'll get the peak where exactly this topological change is happening. So that's the advantage of, or the motivation behind working towards this direction of computing the topological distances, which is the distances between the topological skeleton or the abstraction from the data. Okay. So topological skeletons and the distance between them is more effective as compared to that ordinary distances. So topological skeletons for the scalar data, it's originated from the Morse theory, right? So Morse theory is giving you some kind of skeleton, which is the graphs kind of skeleton. It's not like the graph of a dynamical systems, whatever you have seen in the morning. So that's more kind of complicated graph. But here in the Morse theory, we consider the Morse functions, which is all types of non-degenerate criteria we are assuming on the function, right? So there we can assume that the critical points are non-degenerate, and so Morse theory is saying that the topological changes on a surface will be can be detected by by computing the critical points of the Morse function defined on the surface. So that way, so if we consider the or compute all the critical points corresponding to a Morse function defined on a surface, so then we would be able to compute a graph which will be capturing the topological changes on this surface, right? So that's the change in the level set in the of the function defined, or the level set corresponding to the Morse function defined on this surface. So that actually captures the change in the level set topology, where each connected component of the level set will be called the contour. So this is one skeleton, which we'll see that how this skeleton is used to compute the distance between two scalar fields. And so this is a particular type of rib graph where we consider the domain as the contractible or simply connected. So that will not have any loop, and we call this contour tree, which is mostly used for different types of scalar fields, which is coming in a domain which is contractible. Okay, so that will be without any loop. So this is the first technique which came in 2001, and it was very successful that time for computing the distance between two shapes, the topological distance between two shapes, which was proposed by Hilaga et al. In 2001. So what they do, they compute the multi-resolution rib graph by subdividing the range of the shape, or if we consider some kind of Morse function or the height field corresponding to the shape, and then you subdivide this and construct the corresponding rib graph. For example, it is showing here in this figure that this multi-resolution rib graph corresponding to this resolution is just a node which is corresponding to the whole data. Then we subdivide it further into two levels. So we get the connectivity between this one and this one and this one, which is giving you this graph, and so on. You subdivide it further, and you get a more finer resolution graph, right? So this series of graphs at different resolution is your skeleton to capture the topology corresponding to the shape, and you use this to define a distance, topological distance between two such multi-resolution graphs corresponding to two such shapes. Okay? And so while designing the distance, you need to keep certain constant, of course. For example, whenever you are finding the distance between this rib graph, multi-resolution rib graph R and S, so we'll be matching two nodes from this multi-resolution rib graph to the here if their parents have already been matched, right? So that's the first condition you need to consider. So whenever we are matching a node and pairing a nodes for finding the distance, then their parents must have matched. And the second thing is that it's called the topological consistency, which is saying that if some nodes are matched between two branches of the corresponding rib graphs, all other nodes on those branches also must be matching. So then only the topological consistency we can maintain, right? So these two are the important. So there are more details, but overall, these two are the kind of the important condition we need to maintain when we are pairing the nodes between the first MRG and the second MRG. So once we have all the pairs, that which of these two nodes will be from two different MRGs will be matched, then we can set different attributes. Attributes means that corresponding to each node will be assigning some sort of area corresponding to each node, or some other attributes like the Betty number or the length of those corresponding to these nodes. What are the lengths of the corresponding the part of in the domain? So if we set all these different attributes, then we just then sum them off to get the final similarity or the distance between the multi-resolution deep graphs. So they showed it that corresponding to if they are considering the geodesic distance as the Morse function or the function as the which they can consider on each of these shapes, then if they compute the MRGs and finding the distance between them using this technique, they can find the similarity between the topological similarity between the key shape and some kind of shape database very nicely. So in fact, they also show that so their distance function, the similarity metric, is rotation invariant, right? So that is not depending on the rotation, and because if they just rotate the shapes, so the value will more or less remain the same. And so this is one of the very earliest technique for finding the distance between topological distance between the two shapes or the data. So this is another similar technique. I'll skip this method because this is very similar. Only thing is that instead of the shape here, they consider the volumetric data. Volumetric data means it will be, these reef graphs will be the contour tree without any loop. So this one came by Zhang et al. In 2004. And so they basically consider the similar, like the multi-resolution deep graph, they consider this multi-resolution dual contour tree. And then they find the distance between such dual contour trees using the similar technique, like whatever we have seen in the previous technique. So there are a few other techniques. I'll just show you one more. So this is a data set they applied for this volumetric data using this dual contour tree. One open question in this paper is that how to, so here they are actually using some kind of protein molecular data to find the distance between between the protein molecules using this dual contour tree distances. But so here they are using only the scalar field like electron density and electrostatic potential. So these two are the some electrostatic potential of the one of the protein molecule, and this is little bit noisy data of this one, noisy version of this data, and then they are finding the distances in this distance table. Similarly, this is for electrostatic electron density data corresponding to a protein molecule, and similarly for this one, and this is a rotated version of this, and this is with different resolution. That's how they are getting two different data set from the same protein molecule for these three protein molecules. So what they have observed in their experiments is that so using only one scalar field, they are not able to distinguish different types of protein molecules very nicely. So one of the open question was in this paper was how to correlate this electron density and electrostatic potential fields to finally distinguish between different protein structures. So that means that the use of multi-field was realized from 2004 that that using only scalar field, only one scalar field may not be able to give you the right way to distinguish between two different protein or the two different shapes. It's quite intuitive also, like if I just try to measure some object using suppose only by length. So, and if I also try to characterize that using length and width, of course, the length and width will be giving you the better idea about the object, right? So it's a similar kind of intuition that if you want to use, finally distinguish different shapes or the data, so you need to apply different multi-field, different scalar fields and need to design those methods for multi-fields. So one final method I'll talk, so this is also quite well known. So using the persistence diagram. So persistence diagram actually can be motivated by capturing the topology on these mountain ranges, right? So you can see this, it actually captures the prominence of the peaks in a mountain range, right? So it's like the height of the summit above the lowest contour line, encompassing it without enclosing any higher peak, right? If I consider this one, so the peak corresponding to this one, but not this one. So that's the thing, it's been captured in the persistence diagram. I think most of you are familiar with the persistence diagram. So this is another motivation for getting how we are actually, what exactly we are capturing in the persistence diagram. And the distance metrics are very well known for the persistence diagram. For example, this the bottleneck distance between two persistence diagram are basically, you need to match two persistence diagram corresponding to two different scalar fields, and then you need to do some sort of matching of the points. There are algorithms corresponding to this, which I'll not go into the details. And then you find the, for all such matching, you will be finding the distance, and then you take the infimum over all sort of mappings possible between these point clouds, right? So this is called the bottleneck distance, and similarly, it can be generalized for the Wasserstein distance. And the Cohen-Steiner in 2007, they have shown this. This is satisfying the stability property. Stability property is one of the important property what we kind of impose, whatever the distance you will be proposing new from our own. So you need to characterize that your distance is satisfying some sort of stability, or whether it is satisfying some metric property, right? Metric property is also is known to us that it should be satisfying this non-negativity, then symmetry, reflexivity properties of this. So this two distance function between the persistence diagram will be satisfying this property or metric property and the stability property. Now, the stability means that if we perturb these scalar fields, underlying scalar fields little bit, so it will not change the underlying the persistence diagram drastically, right? So the bound between this change can be the bound between the distances between the persistence diagram would be bounded by the distance between the underlying fields, right? So if you change those fields little bit, then this change also will be bounded by that change. So it will not change drastically. Then it will be of no use unless it is of stability property. And that's the main reason why this bottleneck distance or the Wasserstein distance is so popular in machine learning and also in the data analysis. So one sort of extension of these distances, we see, like I talked about the Reeb graph corresponding to a shape. So if we compute a Reeb graph corresponding to a shape, and then we apply some filtration on the Reeb graph, that also will be giving some sort of persistence diagram for different in different dimensions, like ordinary and extended persistence diagrams of different dimensions, and we can finally capture all this persistence diagram into a single persistence diagram to represent all the topological features in this corresponding to this graph. That will be also giving you some sort of topological descriptor corresponding to the underlying shape or the underlying scalar field, right? So this is another representation, and then there is also Wasserstein distance between such persistence diagrams corresponding to the Reeb graph. corresponding to, there is another layer of abstraction I am including here. First, from the shape, I am considering leaf graph, and then I am considering the persistence diagram. And then this distance is well defined. So this is also satisfying some kind of pseudometric property. And this will be giving you some distance between the underlying shapes or underlying data, right? But this is all, I mean, so far, whatever the three techniques I have shown, so they are all for the scalar field. And so what we want to understand from here, there are also actually many other techniques for computing the topological distance between the scalar fields. For example, so these are few of them, like Jayawardene given this graph edit distance, then extended branch decomposition graph was proposed by Saiki et al. And Vijay Natarajan and his group was working on the distances between extremum graph and then edit distance between merge trees. So, and they were also detecting some kind of topological change in a series of data by applying this data. So all these are for this scalar field, and there are many others. Just to name a few, these are actually mostly used distances between the scalar fields. So the next part of my talk will be that why we should be going to multi-field. Research gap is what I have already discussed, that not all features in a data can be described by scalar topology, and requires multiple scalar fields to describe the topological features in the data. Okay. For example, in this paper by Duke et al. 2012, they were experimenting with that data set with the fermium and the plutonium atom data, with the time varying data, which was they are trying to find where exactly nuclear scission happens in this data set, time varying data set. And but there they were not using any distance function for every timestamp, whatever they had, the data they had. They're trying to find some kind of topological skeleton and trying to visualize it manually to detect where these topological changes are happening. Like they were finding some topological abstraction corresponding to this, which is called the JCN, the joint contour net, and they try to find that where this scission happens by looking some kind of fork-like structure in their net structure. So that's actually difficult to detect it manually. And but another thing they observed in their experiment, if you are computing just using only the scalar field, if you are computing some kind of topological skeleton like the contour tree, so that won't be able to detect this fork in a correct location, okay, correct location where this topological changes are happening. So that's the kind of underlying motivation that why we need to compute this, kind of develop this multivariate or multi-field topological features, and that requires some more kind of development of the data structure corresponding to the multi-field. Another motivation came from the work by this fiber surface, which is another technique for, it's a generalization of the isosurface. Isosurface and the Marching cube are kind of very well known in computer graphics. So we just try to compute the isosurface corresponding to different scalar fields. So given any particular value of the iso value corresponding to a scalar field, we can find its level, right, using this Marching cube technique. So this part of this picture is showing the isosurfaces corresponding to the electron density of the ethanediol molecule. Ethanediol molecule, we are considering the electron density and reduced gradient here. So corresponding to two of these scalar fields, they find the isosurfaces for different levels. And the right side is a new technique where we look these two scalar fields jointly, and that is called the fiber surface. So I'll not go into the details of how the fiber surfaces will be computed. So, but that is actually the technique for finding the isosurface equivalent corresponding to the multi-field. okay, which are called the fiber surface. Now, using the fiber surface, you see that we are able to detect the more features which are not coming using the isosurfaces. So these are the features which are called the non-covalent bond in this data set, which is possible to detect only using the fiber surface. So that's another motivation why multivariate features will be giving you more important or the more sophisticated features which are not possible using only one scalar field. So I'll now discuss a couple of the recent contributions in this domain of computing the distances between the multi-field topology. So so basically the techniques we have discussed for the scalar field, like this MRG, the multi-resolution Reeb graph, and the dual contour tree. So that has been extended using a technique called multi-resolution Reeb space, which is the generalization of this multi-resolution Reeb graph from this corresponding to a multiple scalar fields or multivariate field. And so this is a kind of a technique which is little less sophisticated, but still it does work. This is called the two-dimensional histogram, or this using this technique called the fiber component distribution, or the kind of fiber component histogram. And there is another technique, this one is called the multidimensional persistence diagram. So it is basically the generalization of those persistence diagram corresponding to the Reeb graph for multiple scalar fields. Okay, so we'll just try to see that how people can come up with this kind of generalization for multiple scalar fields instead of a single scalar field. So first of all, so in this for computation of the Reeb graph, we have seen the level set topology, right? We are computing the different levels, level set corresponding to a scalar field, and then finding the topological changes in the level set and finding the some kind of skeleton like Reeb graph. So for multiple scalar field, but for example, the bivariate case, we are showing this picture for the only for two fields here. So how you will be able to compute such kind of topological skeleton? So we consider the level sets of the individual scalar fields and take their intersection. So that is these black curves basically, and so they will be represented by a node in this topological skeleton. So each node here corresponds to its black curve here, which is the intersection of two scalar fields. Intersection of two scalar fields here, they are considering the scalar fields as the same scalar fields what we have discussed before, like this height field and the paraboloid field. And if you take the intersection of this height field level sets and the paraboloid fields level sets, then you will be getting this kind of circular curves, and you compute the neighboringness of those curves and capture this in this kind of topological skeleton, which is called the quantized Reeb space. Quantized Reeb space is the generalization of the Reeb graph. And if we consider, say, three fields, so then you will be getting some 3D structures here corresponding to each of these seeds. So that will be more complicated to visualize. So here, that's why I have considered only the two fields where you will be having these two-dimensional seeds. Okay. Now in this, so similarly, like in Reeb graph nodes, so here we'll be having the singular nodes, which are called the Jacobi structure, where this topology of this structure will be changing. For example, if you try to relate this with this data set, the middle part of this will be related to this. So basically, this fiber components or these black curves are actually growing from this bottom part, and then So it will be growing, then touching the boundary, and then splits into 4 different components, right? So the same topology has been captured here. So these are the nodes corresponding to these black curves in the middle. You can see match the color map corresponding to this one and this one, and then they will be coming in the boundary, this black curve which is here, and then they will be having 4 spread along these 4 sheets. That's how this is kept. This skeleton is actually capturing the topology of these black curves here. Okay, so that's the kind of underlying intuition that how we are getting this topological structure using this. So the algorithm part, I'm not going into the details. I'm just trying to show you the relation between this data and how we are getting this topological skeleton. And critical nodes also can be computed from this skeleton, which are called the Jacobi structure, which will be kind of, you can see it from the next slide. So these are the critical nodes, which are also very important to understand the where exactly the topology is changing in this data. Okay. So the first technique, what Agarwal et al. Had shown, so this is basically they are computing this individual isosurfaces and this corresponding to this F1 and F2, the paraboloid field and the height field, and then taking the intersection between these, which are these black curves, which I have shown in the previous slide, and then they compute this topological skeleton from here, and finally they project them into a 2D histogram of all these nodes, because each of these nodes are having some kind of value, right? So that they project it to get a 2D histogram, and we know that how to find the distances between 2D histograms if we are given 2 such data set. Right? So that's a very simple technique. So why they are considering first this 2D histogram? Because of that reason that computing the distance between the Reeb spaces is challenging. Because previously we are considering only a Reeb graph and finding the distance, and whenever we are considering the Reeb space, finding the distance between 2 arbitrary Reeb spaces is not so easy. In the beginning, they thought like that way. So, but this also, I think for this Reeb space, 2D histogram, the distance can be found point-wise by the point-wise matching between the histograms, and then find the distance. And they also include the critical nodes, giving the importance of the critical nodes in this distance metric. And they shown that this satisfies the metric property, although the stability property is not shown in this work. Okay. And applied it into different kind of data set, like this nuclear fission data, what previously been shown in 2012 paper, only using the visualizing this this net-like structure, and by observing the fork in that. So that has been automated by this distance function. By looking at the peak in this distance plot, they are able to detect the correct point of the nuclear fission point, where the nuclear fission happens for this plutonium atom data. And similarly, another data like fermium atom data also, they are able to relate this with this the highest peak with this distance plot. Although the plot for the fermium atom data is not so prominent, I would say that, because there are a lot of other peaks are coming. But still, I think the maximum peak what they are getting from this plot, it is detecting the correct nuclear fission point for the fermium atom data nicely. So that we'll see in another technique, that how we can get a better distance plot. This is coming because the histogram, you know that whenever we are projecting the sheets in the histogram like thing, a lot of topology is lost, right? Histogram actually will be losing those information which is there on the sheets of the Reeb space. Whenever we'll be projecting it, it will be lost, and because of which this plot is not so nice, but still it is useful to detect the correct nuclear fission point of this fermium atom data. The another data set what they are using is this is called the platinum and the CO molecule, so from the series of data set, they wanted to detect where this kind of stable bond is formed at this timestamp of I think it is 20 or something. It's around this timestamp. So this is happening at timestamp 20. Some stable means it is of smallest length and it will not be changing that much after this bond formation is happening. So that is also been detected by the highest peak, although some more peaks are coming, but it is detected from the highest peak in this distance plot, whatever they've been shown. So this is the second method, which is generalized from this multi-dimensional or multi-resolution RIB graph to multi-resolution RIB space. So there we have seen that how they are computing the multi-resolution RIB graph as a series of RIB graph in different resolution. So the same technique can be extended to compute a multi-resolution RIB space for two-dimensional data set. Like here, this is showing that multi-resolution RIB space at the full resolution, at the coarsest resolution. Then when we are subdividing into this resolution 2, so that means the connectivity between the nodes will be giving you the corresponding RIB space, and which is consisting of these nodes with two field values. If there are three field values, we'll be getting three field values here. If there are R number of field values, we'll be getting R values here. That's how this paper is actually generalizing the multi-resolution RIB graph to multi-resolution RIB space, that this structure, this data set at different resolution and their topological property been captured in this series of RIB spaces at different resolutions. And okay, so next question will be, how do we pair this multi-resolution RIB spaces corresponding to two different multi-resolution RIB spaces? So the same technique, whatever we have seen, this parent-child relationship and then this topological consistency, that should be matched whenever we are pairing two RIB spaces. The nodes from the first RIB space and the nodes from the second RIB space will be matched only when these two relationships are actually satisfied. Like one is the parent-child relationship and that is the topological consistency. So I'll not go into the details of that technique, that's little involved, but so basically they construct a multi-dimensional RIB graph by decomposing this multi-resolution the RIB space, or we call it also the JCN, the joint contour net, they decompose this into multiple RIB graphs. The first dimensional RIB graph based on the first scalar field, then the second dimensional RIB graph based on the second scalar field, and so on. And when we are considering two such RIB spaces, then the matching will be done based on the property by parent-child relationship and this topological consistency. And here we mean the topological consistency, like we have seen that if we are matching the nodes from two branches from the multidimensional from the RIB graph, then the other nodes in that branch also should be matched, like this one. So similar, like whatever we have seen in the multi-dimensional, in the multi-resolution RIB graph. So that's the technique being generalized here. And application-wise, so then the computation of this distance function from corresponding to two different multi-resolution RIB spaces is kind of the similar, like whatever the way they computed the distance between two dual contour tree, or the distance between two multi-resolution RIB graphs. So corresponding to each pair, they find the attributes and then do this kind of calculation and then sum them up to find the distance between them. Okay, and so this distance function between two multi-resolution brief spaces satisfies the metric property, but still there is a gap that it is experimentally showing that it is satisfying the stability property, which is one of the important property, but still it is not theoretically been proven in this paper that it is showing the satisfying the stability property. Whereas experimentally you can see that as compared to the previous method, like this 2D histogram method, for this fermium atom data, where we had seen a lot of extra peaks, which was little bit kind of coming because we are projecting the deep space on the two-dimensional histogram on the range. So here the peaks are quite prominent, corresponding to the change in the topological change in the data. So this is the data set what they use, this fermium atom data, and they want to detect this topological change at this timestamp where it is happening. And that has been detected from this the distance plot here. So that is the correct distance plot they are able to detect using this method. So the final metric what has been recently been proposed between two multifields is, so this is the corresponding metric plot. You can just see the similarity metric plot corresponding to those the same data set whatever been shown here. So the last one is the extending this persistence, the multivariate to the multivariate persistence one. So this is the final kind of the distance what I'm going to show you today. So in general, we do not have any multidimensional persistence diagram as we have seen the persistence diagram, right? Corresponding to a scalar field, we have a persistence diagram, but we do not have any multidimensional persistence diagram corresponding to if we consider multiple scalar field. So, and the motivation came from like whenever we are trying to find some kind of investigate the temperature pattern in a mountain range where this is over all the mountain range and where this altitude and the latitudes are changing, you will see different kind of temperature pattern, right? Because only looking at the latitude or the longitude, you won't be able to get the correct pattern. If you consider both, perhaps you will be getting a better pattern of the mountain field. And that is the motivation behind that why we are detecting or working in this multidimensional persistence diagram. And so the idea is simple, like corresponding to a bivariate field or the multiple field. So we can compute the corresponding Reeb graph. We are not going directly from the multi-field, but first we are constructing a multidimensional Reeb graph corresponding to the multi-field. And then corresponding to each of these Reeb graph in this multidimensional Reeb graph, we compute the corresponding persistence diagram as I had shown in one of the previous slides. So how they are actually combined into this single persistence diagram corresponding to this multi-field or multidimensional persistence diagram. You look at the each of the points in the persistence diagram and see its lifespan. See the lifespan corresponding to these points, like this is in 1, 5. And in this lifespan, you look at what other topological changes or kind of topology being captured by the other persistence diagram. So you basically combine each of these points in the persistence diagram corresponding to the Reeb graph, corresponding to the first Reeb graph, with the Reeb graphs in the second dimensions, which will be capturing the persistence diagram which will be obtained from the second dimensional Reeb graphs, and you just combine their persistence points to get the single persistence diagram, which we call the multidimensional persistence diagram. So within the lifespan of each of these points, we look at the other persistence diagram and basically combine the points in this persistence diagram, and that will be captured in a single persistence diagram. That is the persistence feature captured for this multifield. Okay, and that is the topological skeleton. We call it the multidimensional persistence diagram. And then finding the distance between two such persistence diagram been captured by the similar kind of distance function, whatever you have seen for the persistence diagram corresponding to the Reeb graphs in one of the previous slides. Right? So these are the Reeb spaces, or the corresponding to two different multifields. Multifields are having two scalar fields, and then you compute the persistence diagrams, the multidimensional Reeb graphs, and then find the persistence diagram, and then you combine this persistence diagram to get the distances between two multidimensional persistence diagrams. So matching criteria is a bit involved, but here also we need to consider some sort of topological consistency and dimension consistency, because you cannot just match the dimension of and the point dimension in one persistence diagram or with a point dimension with different persistence diagram. So those criteria has to be matched. And so this metric is satisfying pseudometric property, not the metric property, because as we know that two different Reeb graphs can have the same persistence diagram, that will violate the this identity property in the metric property. So that's why we are getting the pseudometric property. So this will be giving not the metric, but one small property will be less, the pseudometric, but it is satisfying the stability property. So that has been proved in the paper, in this paper, that this is satisfying the stability property. And this has been used for different shape matching problem, similar as in the first paper in Hilaga et al. And it's showing that it is able to distinguish for this data set called the shape retrieval data. It is a very standard data in the graphics community. If we use this data, and these are the plots, the similarity matrix plot or the distance metric plot corresponding to these shapes, using this only one scalar field, which is called the normalized geodesic distance. This is also the normalized Euclidean distance. So that's the plot. And it's not able to distinguish the shapes from the other shapes very nicely. If we just use only one scalar field from the similarity metric plot, you can say. Whereas if because here all are kind of very low values, so this is also, these two are also showing the low value, right? But whereas if we use these two fields together and then compute the multidimensional persistence diagram and then use the proposed distance metric, then that is able to capture this clustering of those distances, the similar kind of shapes nicely when we are using this multiple scalar field or more than one scalar field. So that's the advantage of using this multiple scalar field and the corresponding distance plot. And it has also been shown applied for the similar data set for these three fields, and for this data set called the Homo-Lumo data set. And okay, I'm skipping this because of lack of time. And so it has been shown that using one scalar field, it's not able to show the correct kind of change in the topology in this data set. Whereas if we use these two fields together, then it is able to find the correct clustering on this data set for this bivariate, for the bivariate fields. So in summary, we just have seen that why topological distances are important than the ordinary distances. Then we have seen that computing the scalar topological distances based on this multi-resolution Reeb graph, then dual continuity and the persistence diagram based on these three data structures. And then we have also seen some motivation that why multi-field topology is more important than the scalar topology, and some of the recent contribution based on 2D histogram, multi-resolution deep space, and multidimensional persistence diagram. And conclusion that we have seen that topological distances are more important to detect the topological features from the data, and multi-field topology is more effective than the scalar topology from the experimental evidence I have shown to you. And some of the open problems are still people are working. So to capture, because this multi-resolution deep space is currently just capturing one type of topology. So the fiber surface topology is still not yet captured in any kind of data structure or a skeleton. So that's one important open problem in this domain. And generalizing this MDPD, like multidimensional persistence diagram, currently computed from multi-resolution deep graphs. So can we have some kind of similar abstraction directly from the data without constructing this multidimensional deep graph in the intermediate data structure? So that will make it even faster. So that's the kind of another open problem in this domain. Thank you very much for your kind attention. If you have any query, thank you.
Questions, please.
Yes. 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 So yeah, so there is some matching algorithm how we will be computing the matching over all such actually you have to, but so in the matching algorithm which is there, so that will be making it kind of computable for this bottleneck distance. Okay, I'm not going into the details of the algorithm. The algorithm details is little involved, but you can find some kind of bipartite graph by which they try to match and find the bottleneck distance for all of our functions. Yes.
I have one question.
Yeah.
So the distance between the multidimensional deep graphs that you showed, is it a computable distance?
Yes. So basically it is computable because we are computing this multidimensional deep graph for finite resolutional deep graphs, right? It's not for infinite resolution. So whatever the computation we have shown here, that is for finite resolutional deep graphs. So
there is
it's
like
computationally expensive, I agree, but it is computable.
So there is a discretization of the range space.
Yes, exactly.
Okay.
Exactly. And with finite number of resolutions. Okay.
Thank you.
So yeah. So the complexity, another thing, I didn't go into the details. It is there in the paper. It is computationally depending on many factors like the resolutions and number of fields and number of critical points in the data. So it is a bit complex to decide that what will be the complexity, but still it is shown that it is computationally possible. Stability of this metric, how? So like stability means whenever we are considering the, like for this persistence diagram, corresponding to two scalar fields, we have two persistence diagram. Then suppose you are computing the bottleneck distance between the persistence diagram. This bottleneck distance between the persistence diagram corresponding to persistence diagram, theoretically it is proved that it is bounded by some kind of infimum norm between the functions. So that means that if you perturb the function little bit, so the corresponding distance between the persistence diagram will not change a lot. So it is bounded. It is not exceeding that the bound between the functions. Okay, so that's the stability.
Any other question, please? No further question. Let's thank the speaker for a very nice presentation.
Thank you.
Thank you.
Now I invite Krishnamurthy sir to hand over the memento to Amit Chadhyapate. thank Krishnamurthy sir for chairing this section.
Next session are invited talks in parallel, starts at 3:30. In this hall, we'll have invited talks by Dr. Siddharth Pritham and then by Sramrudendu Shekhar. In the other hall, we'll have invited talks by Dr. Vishnasi Narayanan and then by Dr. Manigandan Dangasamy. We'll break for tea and rejoin at 3:30.
Samit for the introduction, and thanks Professor Vinod for inviting me and for the warm welcome at the Institute. So I'm going to talk about topological data analysis, and I hope you are not bored already because we had 2 talks talking about, sorry. Better? All right. Yeah, so I hope you're not bored. So the plan is as follow. I'll briefly speak a little bit about broader perspective over data analysis, and then introduce topology, and then go to topological data analysis, and then computational aspect of it. So the talk will be focused more on algorithmic aspect of topological data analysis. Okay. So data analysis could be thought of as extracting information from the data, and information could be realized as a sort of manifestation of relationship between elements of the data. Okay. And this information will depend on how we look at the data. Right? So you can think of data as a point cloud. For example, here points in R2, and we can look at the relationship, geometrical relationship between points, statistical relationship between points, and these relationships will manifest in different types of data, information. All right. So the idea is to learn about this information, capture this information through various tools, geometric tools, topological tools, algebraic tools, right? So in this talk, we will focus on topological tool. The reason behind that, we want to understand more sort of global information out of data from the local given information, okay? So in analyzing these relationships, we can have, broadly speaking, 2 problems. One is the problem of size. So we can have huge data, high dimensional data, and there are algorithms to tackle them. And then the complexity of data. So you can characterize complexity in a various way. One of the ways to look at the shape of data, which will give you idea about the complexity of the data. Okay, so we can look at these 3 examples. So here we have, point set sort of more in a linear fashion. So I can capture the shape through one equation, one linear equation, and I know the sort of the detail, not details, but I know the shape of the data. If you look at these 2 this point set, it's a bit more complex than this one, because you can't have a one line which sort of gives you information about the data set. So you can cluster them, and each cluster can be represented by one point. So you need 3 points to characterize these data set. This one is a bit more complex. So it's a join of 2 circles, right? So you need a sort of degree 2 equation, polynomial equation, to capture these 2 data, this one. And not just one equation, you need 2 equations sort of, and they're join. Okay, so you can see that the shape, their shape are different, and the shape is sort of characterizing the complexity of the data. And looking at shape implies, topology implies studying the shape, and that's why we are choosing topology here. And you have already seen, in 2 talks, how looking at the shape of data is very useful from data analysis perspective. Okay, so before moving further, I would like to introduce this object simplicial complex, which is sort of generalization of a graph. So in graph, you capture pairwise relationships. So each edge in a graph is sort of represents a relation between these 2 points, right? So if I want to capture k-wise relationship, if I want to understand the relationship between 3 points, then I need to include a triangle. If I want to represent relationship between 4 points, then I could represent that using a tetrahedron. So likewise, this set of faces, which are called simplices, edges, triangle, and tetrahedron, if they are nicely glued, this is called simplicial complex. Okay, so nicely glued means that 2 simplices intersect on a common face. They do not intersect in an ad hoc manner. All right. So this is a simplicial complex which captures k-wise relationship, and this is the primary object onto which we will perform our computation. So, so once we have this relationship captured through simplicial complex, we can sort of endow a lot of mathematical structure on top of these simplicial complexes and then study the relationship through those mathematical structure. For example, you can look at the simplicial homology group, you can look at the sheaf, you can look at the Laplacian, a filtration, discrete Morse function. So these are the mathematical things which you can endow and then learn about the relationship through simplicial complexes. So one example is persistent homology. This is a very rich area of research, emerging, I can't say anymore emerging, it's more or less established. And it has problems from mathematical structural point of view, algorithmic problems, and applications. So topology, I think more or less you know everything about topology, but just for the sake of completeness, I would briefly go about what topology is. So it's a qualitative form of geometry where we are not concerned about distances and angle, but overall connectivity of the object. So for example, these are geometrically different, but topologically equivalent because they have the same connectivity, same number of holes. So to understand a bit more, these two graphs have the same number of vertices and same number of edges, but they are differently connected. One has one connected component and the other has two connected components. Okay, so this is captured by what we call zero-dimensional homology. Okay, so homology is a mathematical framework to capture the connectivity, and here we say that these two have different zero-dimensional homology because they have different number of connected components. Another example, we have this graph. Now both have same number of connected components, but one has a cycle, another does not have cycle. And this cycle is one-dimensional because what bounds it is one-dimensional. Right? These edges are one-dimensional thing. So this is they are different in terms of having one-dimensional holes. So now, so this is captured through one-dimensional homology or one-degree homology. Okay. So in general, homologies are vector spaces. So you can generalize the idea and look at k-dimensional homology, and they are vector spaces, and their rank is called Betti numbers. So the rank is basically telling you how many different types of k-dimensional holes are there in the topological space you're looking into. Okay. Another example is a torus and a sphere. So here, if we look at the Betti numbers of sphere, beta 0, which is the rank of zero-dimensional homology group, is 1 because it is one connected component. Beta 1 is 0 because it is simply connected, meaning that there is no non-trivial loop on the surface of sphere. Beta 2 is 1 because you have one two-dimensional hole. All right? And higher degree betas are 0 because we have just two-dimensional surface. If we look at these numbers for torus, beta 0 is one connected component. Beta 1 here is 2. Essentially, these two loops are two non-trivial loops on the surface, and they are different to each other. So that's why beta 1 is 2, and beta 2 is again 1, which is the cavity which captures the cavity enclosed by the surface of torus. Okay. So you can see that these two are, their Betti numbers are different, which means that they are two different topological spaces. So using Betti numbers, you can distinguish between topological spaces. So they are weak topological invariant in the sense that if you have same Betti numbers, you can't say that the two spaces are same. But if they are different, then you know that they are different topological spaces. So we will use Betti numbers to distinguish topological spaces. So that's the idea. So now let's look at topological data analysis, and the most used tool in TDA is basically broad term for using topological methods for data analysis. And one of the method is persistent homology, which is sort of most widely used. So the problem is as follows. I have a topological space X, And I don't know the whole space X. I just know the finite sample of X. And there is a hypothesis that X might be some sort of nice manifold or things like that. And I want to understand the topology of X through P. So precisely, in particular, I want to understand the Betti number of X through P. Okay. So the problem is that you have local information about the points, and you want to understand the global connectivity of the space. So one probable intuitive idea could be that we look at these points and we put Euclidean balls centered at these points of certain radius and look at the union of balls. Okay, for example, you have here 3 different scales of Euclidean balls, and at a smaller scale, the union of balls are sort of not connected. Right? There are different connected components. If you look at the union of balls at a medium scale, they form one connected component, and it looks like they are homotopy equivalent to a circle. At this scale, everything kind of mixes together, and you have a disk. So if you just eyeball this example, it looks like these points are coming from a circle, and at the middle scale, the union of balls are able to capture the topology of the circle, right? So the problem could be thought that if we know the right scale, right epsilon parameter, we should be able to know the topology of X, right? So you can think of this as a problem of how to find the right epsilon. But the problem is a bit more involved. So to understand this, let's look at this example. Now here we have a smaller loop and a bigger loop, right? And if we look at the union of balls at a smaller scale, the smaller loop is captured, right? If you look at the union of balls at a larger scale, the larger loop is captured, but both of them are not captured at one scale. So you can't capture both simultaneously. Right? So this implies that there is no one right epsilon, which will give you the topology of X. So how do you resolve this problem? So essentially, what we can do is that we can look at the union of balls at multiple scales, right, and track the changes in topology as the scale increases. And this is the idea behind persistent homology. So let's look at another example to understand what persistent homology is. So you have this point set, right? In the beginning, we have balls of radius 0. So each point is one connected component. So here we represent the connected component through these bars. Okay, so the horizontal line is the scale parameter. So at this scale, each point is represented here as one bar, one connected component. If I increase the radius further, I get, some of these balls start intersecting, and then they form one connected component. So at this radius parameter, I have only 5 left components. 5 components are left. Right? So some of these bars have stopped, moving further. So they merged into one of these longer bars. Okay? Now, if you increase the radius even more, all of them have intersections, so they form one connected component. So there is only one red bar at this scale, and you can see emergence of 2 loops in the data. So these are one-dimensional feature. They are represented by the blue bars. So at this scale, I have one connected component and 2 one-dimensional loops. If you increase the radius a bit more, the smaller loop disappears, and the bigger one is still present. Okay. So at this scale, I have one connected component and one dimensional hole, right? And at even larger scale, that loop also disappears, and I have only one connected component. Sorry. So at infinity, you have only one bar. So sort of these bars track the evolution of the topology of the union of balls. So the left end of the bar is the birth time of one topological feature, and the right end is the death of that particular topological feature. Okay, so this is called persistence barcode. And the idea is that the smaller bars are sort of noise and the longer bars are the real feature of the data. And it depends on the application. There is an equivalent representation of persistence barcode, which is called persistence diagram. So each bar is could be represented as a point in R2, where the horizontal axis is birth time, birth scale, and the vertical axis is the death. Okay. So since birth is before death, all the points will lie above this diagonal. Okay. So this is called persistence diagram. And they are equivalent representation, and people use it depending on the, they choose one over another depending on their applications. Okay, so this is sort of the conceptual idea behind persistent homology. Now to compute, we need to go from union of balls, which is a continuous space, to discrete setup, which is simplicial complex. So there are various ways which, through which you can compute simplicial complexes over point cloud. There are many which come from the union of balls, and here I present two examples. One is called check complex, and another is called Rips complex. So check complex is essentially the nerve of the union of balls. So whenever two balls have intersection, I put an edge. If three balls have common intersection, I put a triangle. So I explained it before, and this is what check complex is. Okay. So at particular radius epsilon, I get a particular check complex. There is another way to construct simplicial complex, is that we don't look at the common intersection between k many balls. We just look at the pairwise intersection. So whenever I look at 3 points and they have pairwise intersection, I put a triangle. I don't wait for them to have a common intersection. So you can see in this example is that these 3 balls are not intersecting here. So check complex does not have the solid triangle represented by the yellow color, whereas the Rips complex does have a solid triangle. So clearly Rips complex does not capture the topology of the union of balls, whereas check complex is homotopy equivalent to the union of balls. Okay. So why one prefers Rips, why one chooses one complex over another complex? The reason for check complex is, of course, the topology equivalence, and for Rips complex is the ease of computation. So to compute check complex, the complexity is exponential in terms of the ambient dimension, whereas to compute Rips complex, you only need to know the pairwise distances. Okay, so it's easy to compute the Rips complex. And this is an example of a flag complex, or also known as click complex. So the whole complex is represented using the underlying graph, one skeleton. So even to store the Rips complex, you don't need to store the whole simplicial, all the simplices of all dimensions. So this is why computationally Rips complex is much more efficient. And if we look at from the perspective of persistence computation, we don't lose a lot in just computing Rips complex, because the check complex and Rips complex satisfy these interleaving property. So if you look at Rips complex at 2 different scales, so one epsilon, another √2 epsilon, the check complex at √2 epsilon will be a subcomplex sandwiched between these two. Okay. So when you increase the scale of the balls, they both will sort of vary in the same way, the check complex and the Rips complex. Okay. So as I increase the radius of the balls, we get a nested sequence of union of balls, right? The space forms a nested sequence, and correspondingly, the simplicial complexes, whichever you form, the Rips complex or check complex, they will form a nested sequence of simplicial complexes. And these nested sequence of simplicial complexes are called filtration. Okay. And the filtration value of a particular simplex is the radius parameter at which it appears for the first time. Alternatively, you can think of a filtration as a scalar valued function on a simplicial complex K, which is monotonic, in the sense that if sigma is a phase of tau, then the the filtration value of sigma has to be at most filtration value of tau. So this is filtration. Given the, you can look at persistence a bit more from the algebraic point of view. So given filtration, if we compute the homology group of any fixed degree P, we get a sequence of vector spaces and linear maps induced by these inclusions on the corresponding vector spaces. So you get a vector space connected through linear maps. So this is what we call persistence module, because it has a module sort of structure. And a simpler kind of module is what we call interval module. So here is one example. So interval module between two parameters 2 and 4 is like this. So you have, let's say, 6 length module. So from 2 to 4, I'll put the field in which I'm doing the computation, and rest is the zero vector space. And whenever I have two non-zero vector spaces, I'll map them through identity, and other is 0. Okay, so this is called interval module. And the structural theorem is that any persistence module could be decomposed as direct sum of interval modules, where you have bi and di as two parameters for each interval, and they correspond to the points in the persistence diagram I explained before. So the birth, bi is the birth coordinate of one point in the persistence diagram, and di is the depth of that particular feature in the persistence diagram. So it has very nice algebraic structure as well. Okay. So now, how do we compute these things? So to compute, you start with the filtration. You have a filtration simplicial complex with real valued function on the faces. And given such filtered simplicial complex, you set up a boundary matrix. So the rows and columns of this boundary matrix are the faces, the simplices of the complex, and they are ordered according to their filtration value. So when you move in the column space from left to right, the filtration value increases. And when you move from top to bottom in the row space, then the filtration value increases. Okay. So, and then if a row simplex is a face of a column simplex, you put a value 1. Otherwise, you put 0. So it sort of captures the incidence between the faces. And this is co-dimension 1. So, you put only for edges, look at the triangle, not the tetrahedron. So it's a co-boundary matrix. And here I'm choosing 0 and 1 because in practice, we work with Z2 field. You can choose any other field if you like. So once you have this boundary matrix, you essentially reduce it to another matrix. So the reduction is more of Gaussian elimination kind. And you can see that the algorithm to reduce is very simple. And once you have this reduced matrix, that matrix contains the information about the persistence diagram. So to see that, let's go back. And so what exactly it computes? So if we place the filtration in this manner, so I include one simplex at a time when I go from left to right, you can notice that once you include one simplex, it either creates a cycle or destroys a cycle. So for example, if I have these two connected components, if I put the edge here, the edge merged these components into one component. So one of them died. So this edge is called a negative simplex. Another example, if you go from this configuration, this simplicial complex, to this one, next one, this inclusion of this edge created a cycle, a hole. So this is a positive simplex. Now this hole is killed by this triangle. The moment I included this triangle, this hole disappeared. It became a boundary, right? So the persistence of this hole is essentially the filtration value of this edge and the filtration value of this triangle. So persistence is nothing but pairing of appropriate simplices. Okay. So this pairing is computed in this reduction algorithm. So the complexity of this algorithm is n cube. It's very efficient. And in practice, in fact, it is observed to be linear. So this is one of the main reasons behind the success of the theory, that you have sound foundational mathematical structure and it is easy to compute, which is not so common. Okay. So that's one of the reasons for wide applications of persistent homology. Another reason, as explained by Amit, is stability. So here you have 2 points cloud, let's say X and Y, and if they are close to each other, so if there are various ways to formulate this stability theorem. One way is to look at the Hausdorff distance between X and Y. If the Hausdorff distance between X and Y is close, then their corresponding persistence diagram will have a bounded bottleneck distance or Wasserstein distances. So that's another reason why persistence is useful, because if I perturb my point set a little bit, I don't get something completely wild. Both are related to each other. So it's a stable feature of the data. So now, so even though we have efficient algorithm to compute persistence, but there are still challenges, and the challenge is that the data usually is very large, it's huge, and in practice, the size of simplicial complexes could be of order of billions, especially with the RIPS complex, because the number of simplices in RIPS complex are exponential with respect to the dimension of the simplices. So they grow exponentially. If I compute like k-dimensional simplices, their number is exponential with respect to k in terms of the number of points they look at. So they are basically possible clicks in the graph. Okay. So because of this, computing persistence is still hard, tricky. And especially if you want to compute persistence in high dimensions. For example, if you want to go beyond dimension 3 and 4, it's nearly impractical. Okay. So there are a lot of work in this direction. People try to resolve this problem. So there are two sort of complementary directions in which people approach to solve this. So one is to have a efficient reduction algorithm. So once you have this boundary matrix, there are algorithms which can reduce that matrix in a much more efficient way, in parallel way, things like that. And another approach is to pre-process the input filtration to a smaller filtration, so reduce or simplify it to a smaller filtration in either exact or approximate way, and then compute the persistence of the reduced filtration. Okay. So there are various work in this direction as well. So we, along with my supervisor during my PhD, we worked in the second direction. So we gave a series of pre-processing algorithms based on combinatorial idea of collapses to pre-process the input filtration. So all these work is essentially using various different types of collapses on various different types of filtrations. So I'll explain one of them. I will explain this work with Mark Gliss. So here we use what we call edge collapse. So this is essentially removing certain edges which do not contribute to the computation of persistence. And we identify them through this idea of collapse. So in nutshell, what we do is that we perform three basic operations on the edges. So to go back, I mean, we are doing this work for flag complexes only. So this is this work is restricted to flag complex, and flag complex is, as I said, completely characterized by the graph. So the filtration of the flag complex is essentially the filtration of edges, and then so the filtration value of a simplex, k simplex, would be the length of the largest edge in that k simplex. So once you know the filtration on the edges, for RIPS complex, you know everything. Okay, so we use so we can only work with the skeleton. We don't need to compute we don't need to compute even the higher dimensional simplices or boundary matrix. So this was the salient feature of this work, because previous work required to compute the whole simplex or boundary matrix for pre-processing. And that's why it led to a very efficient method. So again, so what we do is that we basically perform 3 operations, which we call swap, shift, and trim on the edges of the flag filtration. Okay, and so these operations are performed over the graph, and they manipulate the filtration value of the edges. Okay, and eventually we want to manipulate in such a way that we make an edge redundant. So through shifting it across the filtration, I come to an end, and then I find that even in the end it didn't do anything to compute the persistence, so I discard it. Okay, so that's the basic idea, and this results in an equivalent smaller flag filtration, which is important that I get a result as a flag filtration. Because there are many softwares which specializes in computing persistence of flag filtration. It's easier to compute persistence of flag filtration. So the smaller filtration is also flag, which is an important point here. Okay. So how much time do I have? 5 minutes. Huh? 5 minutes, okay. So I don't think I have a lot of time, but I'll just quickly go through the algorithm. So you look at this edge, which is what we call dominated. So you have, you look at the length of the edge, and if the length of edge is a cone, then you can remove this edge, okay? And this removal preserves the homotopy type, which implies that if I look at the inclusion map between the homology groups, it gives me an isomorphism. All right. And another important point is that in the flag complex, I can just look at the neighborhood of the edge in the graph, and I would be able to identify which edge is dominated. Okay, so I don't need to compute the whole simplicity complex. So these two are the important properties which enables us to do this these 3 operations. Okay, so I won't go into the details of the operation, but the algorithm, but essentially it changes the filtration value, and it keeps on moving, increasing the filtration value to the end, and once it can still keep on moving, it removes the edge. So finally it trims the edge. This is the trim operation. So in this example, we needed these 3. So this is the minimal possible edges you require to compute the filtration. Okay. So the complexity of this algorithm is linear in terms of input edges, and cubic in the degree of the graph. So we perform, sorry? K was the degree of the graph. So the number of neighbors of each vertex, maximal degree. So we performed certain experiments to see how our method performed. And so this is the module for reduction of the input filtration, and then we compute the persistence diagram using Goody library. So you can see that many of these computations are being able to done in matter of seconds, whereas if I don't do the pre-processing and compare ourselves with another software, Ripser, which is a specialized software for computing persistence of flag complexes, for the same data set, even dimension beyond 4 and 5, the computation is intractable. So it's mostly because the number of simplices are so high. So Ripser does well for the low dimensional homology computation, 1 or 2, but beyond that, we need sort of some simplification. Okay. So there is more careful analysis done in the paper, but I'm just presenting it here. So yeah, these are the advantages, that you can do everything on skeleton, one skeleton, and the algorithm can be parallelized, and you can also approximate the reduction method, and it is extendable to zigzag filtration, where you not just include simplices but also remove simplices. So your filtration is not going in just increasing; it can reduce as well, and multi-parameter persistence too. So applications, I'll briefly say, I mean, I'm not an expert in this area, but there are, you already have seen a couple of applications. And one way to apply these techniques is that you compute the persistence diagram, and then since the space of persistence diagram is not a vector space, it is a metric space with the bottleneck and Wasserstein distances, but they are not vector spaces. Therefore, you cannot directly apply any machine learning methods on those spaces. So you have to first vectorize them. And there are many methods to vectorize them. And one of them is what we call persistence image. And here what they do is that they first, rotate the persistence diagram by 45 degrees. So that, everything is now on x-axis. So diagonal is the x-axis. And around each point, we define a probability distribution. So these you can choose. And according to that, you give weight to each of these boxes. And then you sum over for all probability distributions. And this basically gives the weight to each voxel here. And what you get is some sort of an image. And the space of images are linear space. So you can now feed this into your traditional machine learning pipeline, and you can use persistence diagrams. There are other methods to do that, kernelization method, landscapes, persistence landscapes, and things like that. But unfortunately, I don't have much time. So there's another application where people are using in EPFL, they have this Blue Brain project where they simulate the brain of a rat through computer, and then they look at the structural changes in the network with respect to different simulations. So these are the different type of simulations, and then that excites the network in a different way. And then they look at the topology of this network, and they are able to distinguish between different type of simulations based on the Betty curve. So they look at Betty curve rather than persistent homology here. Okay. So yeah, so Goody is one of the library which implements a lot of these TDA tools, which you can use if you like. So I thank you for your kind attention, and I'm open to questions if you have.
Okay, so any question from the audience?
Convert persistent diagram into image?
Yeah, I think they have implemented it. This is Henry Adams' work. So
in Goody it is available?
In Goody not. In Goody not. One of actually our master students have also implemented this persistence image computation.
No, the algorithm, whatever you have,
is in Goody.
That is in Goody.
This is in Goody.
Ripsar is not using the same algorithm.
No, Ripsar does not use this.
So Goody is faster than Ripsar.
If you use edge collapser.
Okay, so
cohomology. Homology. Yeah. Yeah, because to compute, you need the vector space structure, because you're performing everything on boundary matrix, right? So you should be able to sum these columns. And no, algorithmically there is a lot of difference. So it's much more easier to compute this way. Even if you go to a bit more complicated field like integer, then computation of these reduction is very difficult.
Any other question? Okay, if there is no other question, so let's thank the speaker again.
Now I invite the chair, Dr. Amit Chattopadhyay, to hand over the memento to the speaker, Dr. Siddharth Preetham. Thank you, Dr. Amit sir, for chairing this session.
Now we have an invited talk by Dr. Amritendu Shekhar on fast algorithms for minimum homology basis. Amit Chattopadhyay will be chairing the session. I invite Amit sir for chairing the session.
Okay, thank you. So, Amritendu Shekhar Dhar, a distinguished individual in the field of computer science and automation. He has been honored with the prestigious Prime Minister's Research Fellowship, currently affiliated with renowned Indian Institute of Science in Bangalore. Amritendu's expertise extends into the realm of scientific visualization, as evident by his notable contribution to a publication co-authored with Lin Yan and Talha bin Mashood. So Amritendu will be speaking today, algorithms for minimal representatives of homology. Over to you.
Thank you. So I talked today about algorithms for
Yes.
Yeah, I hope it's audible now. Okay. So homology, in a very rough way, it's basically helps us in distinguishing the kind of holes in a topological space. So for instance, let's say you consider the annulus and the sphere. The annulus has this one-dimensional hole. The sphere encompasses a two-dimensional void. And that reflects in the homology of the annulus and the sphere. So now I'm wanting to talk about what I mean by representative of homology. So consider this topological space. It's a disk which has two holes in it. And consider the cycle B and the cycle B prime. So both B and B prime are in some sense representative of the same homology class. They both bound this hole. But we'll say that we can at least visually conclude that B is a larger representative than B prime. B prime is smaller or tighter than B. So when I talk of a representative of a homology class, there are in general not one, but there are multiple representatives of the same homology class. So my question is, what do I mean by a tight representative of a homology class? Now we may ask, why do we want a tight representative of homology class? Well, holes in a topological space often represent important features. And it's not just the size and shape of the hole also matters in a lot of applications. So one application that I can quickly bring up is that of zeolites. So zeolites are these materials where they have pores. And often the size and shape of these pores defines a lot of important properties of the zeolites, for example, diffusivity, conductivity, and so on. So to be able to determine the size and shape of the hole is important in a lot of applications. Not just that, the location of where that hole is also important. So homology just by itself is an algebraic invariant. It doesn't tell us the geometric properties of where that hole is and so on. And finally, tight representatives of these holes are desirable to us. So a cycle like B prime is in most applications more desirable than a cycle like B. So let's list down some applications of tight representatives. So here, the first image, precisely this one, this was studied by Wu et al. And they look at something called cardiac trapeculae. So these are certain fibers in cardiac data. And so what they did was that they computed homology 1 cycles, generic homology 1 cycles, and they found out that that was not very useful. But then they tried to compute, there is an echo happening, right? Okay. But then they tried to compute more tighter representatives of those homology 1 cycles, and that helped them to basically identify these cardiac trapeculae in this data. So the ones in blue essentially come from computing tight homology representatives. A second application here is by Emmett et al. And they look at something called chromatin folding. So these are basically 3-dimensional structures in DNA. And the loops and the loops in those structures have these important biological properties. So they need to be able to determine where those loops are located. So again, computing a tight representative of homology was important there. A third application is which is in the area of persistent homology. This was carried out by Luricic. So here it's a typical example of a hurricane data set called Isabel. And so some of the top persistent cycles are represented here. And they often represent properties of what the hurricane looks like, or what are some of the properties of that data set. So when it comes to simplicial homology, it has been discussed before. I'll very briefly touch upon it. So given any simplex, let's say we consider this tetrahedron ABCD, we can consider the boundary of this simplex. The boundary is just the union of the 4 triangles of that tetrahedron. It is generally represented as a formal sum, and formal sum over Z2. And this formal sum can then be extended to linearly extended to not just one P simplex, but a collection of P simplices. So a collection of P simplices, often represented as a formal sum, is called a P chain. A boundary of a P chain is basically what we get after applying this boundary operator. So for instance, if you consider this this triangle ABC, or let's say you consider the triangle A, or let's say you consider this edge AE, then the boundary of this edge is A plus E. Now cycles are precisely those P chains which have an empty boundary. An example would be, let's say you consider the wireframe AB plus BC plus CA. So this is a one chain. But if you compute the boundary of it over Z2 turns out to be equal to 0. Similarly, a boundary is something which is the image of this delta map. So for instance, let's say you consider this one chain AC plus CE plus AE, then this is basically the boundary of this triangle ACE. Now it turns out that basically cycles which are not boundaries are important to us because they represent the holes, or they bound holes basically. And that motivates us to compute the quotient space, which is ZP by BP, is essentially the set of cycles which are not boundaries. That is, they are holes in some sense. We call this the pth homology group. Now the homology group, because we are computing this in Z2 coefficients, this has the algebraic structure of a vector space. Because it's a vector space, we can talk of a basis of homology. So in a slight abuse of notation, I'm going to say that a collection of P cycles, zeta 1 to zeta k, is a homology basis of HP if their corresponding homology classes span HP and are linearly independent to each other. Very similar to how we define a basis for a vector space. So for instance, if we take this, let's say, connected sum of tori, I've indicated these 4 cycles. The 4 cycles, the homology classes of their 4 cycles basically span the first homology of this space. And so that would be a homology basis. Now, when I talk of minimal homology representative, I'm going to talk of three kind of flavors of problems. The first flavor of problem is what I call a homology localization problem. So let's say I am given a cycle, which is a generic cycle, and I want to find out what is the smallest cycle in its homology class. So something like blue would be the smallest homology cycle in this class. The second flavor of problem is what I call a minimum homology basis. So as an input, I'm given a simple shell complex, just a simple shell complex, and I want to compute a homology basis of that simple shell complex, which is smallest in some appropriately defined way. So for instance, let's say you consider the cycles in blue and the cycles in red. The cycles in blue are a smaller homology basis than the cycles in red. We want to compute such the smallest possible homology basis. And the third is what can be called the localized representative of a bar. In this is a specific case where I consider a RIPS filtration, and there are two cycles shown. Both are representatives of the longest bar in the filtration. The cycle in green is decidedly smaller than the cycle in red. So this is of interest to us. We want to compute the smallest representative of a bar. So formally, I can define the problems as follows. So let's say I have a function W which assigns to the space of P chains a positive weight to it. Then the minimum homology basis is defined as saying that we want to compute. Then the minimum homology basis is saying that I want to compute a collection of cycles zeta 1 to zeta BP such that the sum of the weights of these cycles is minimized, and these cycles should be a basis for HP. The localized homology representative problem says that given a P cycle zeta, I want to compute the smallest cycle in its class. So I want to compute the smallest cycle that belongs to this class of zeta. The third problem is the minimum persistent homology representative, where if I'm given a filtration and a bar that belonging to its pth barcode, I want to find out the smallest representative of this barcode B comma D. So zeta prime would be the smallest persistent homology representative of this bar B comma D. So I need to define a minimality criteria. So we previously talked of a weight function. I need to define what I mean by a weight function on simplices. So perhaps the most natural way is the weighted simplex count, which is basically saying that I assign some non-negative, or assign some positive weight to the simplices of a complex, and the weight of a cycle or the weight of a chain in general is just the sum of the weights of the simplices in that chain. So for edges, we can take the length of the edge. For something like higher order simplices, we can take something like the volume of the simplex. But we are going to propose another minimality criteria. So the idea that we have in mind is basically as follows. Let's say I have this triangle, and I want to understand what is the smallest bounding ball of this triangle. The smallest bounding ball of the triangle is going to be its circumcircle. So if we generalize this idea, we can ask if we have a collection of points in some RD, which is a finite collection of points, what is the radius of the smallest bounding ball of this collection of points? I call this the L2 radius of U. For a simplex, the L2 radius of the simplex is just the L2 radius of the vertices of that simplex. The simplex is just because the simplex is a convex structure. And likewise, if we have a chain of simplices, the L2 radius for a chain of simplices is the L2 radius of the vertices which are contained in that chain of simplices. So this is going to be my second minimality criteria, something that we have proposed. Now, how do these two minimality criteria compare with each other? Well, the weighted simplex count, which is the sum of the weights of the simplex, this is there in literature for a very long time, and it's known by different names. It's natural, at least for dimension 1. It has the advantage of being interpretable. But the cons of it comes down to tractability problems. Precisely the minimum homology basis problem is polynomial time only if the dimension is 1. For dimensions greater than 1, for general simplicial complexes, the minimum homology basis problem is intractable for the weight function of weighted simplex count. Furthermore, the other two problem variants that you looked at, homology class localization and persistent homology class localization, they are NP hard for all dimensions. The L2 radius, on the other hand, it captures the diameter of the object. It captures the girth of the cycle. It takes into account the geometry of the ambient space. And furthermore, all the three flavors of problems, the minimum homology basis, the homology class localization, and the persistent homology class localization, they can all be solved in polynomial time. Possible cons of this metric could be like, it depends on an embedding of the complex into an Euclidean space, which such an embedding may not always be present. And of course, some of the exact algorithms, even though they're polynomial time, may actually be slow in practice. Okay, so the minimum one homology basis problem is what we'll study under the weighted simplex count. We just stated that for higher dimension, for homology for higher dimensions, the minimum p homology basis problem becomes NP hard. So here we proposed an algorithm that computes minimum one homology basis for general complexes. So this is the minimum homology basis, but for dimension 1 and for the sum of the weights measured. Before we describe the algorithm, I'll quickly talk about some of the related work. So this problem is a well-studied problem, especially for certain subclasses of complexes like surfaces. There are very fast algorithms. This algorithm runs in almost linear time for general cases. There are also randomized algorithms, and there are also algorithms for general complexes. But what we found was an algorithm which works for all complexes, which is easily implementable, because a lot of these algorithms have certain linear algebra black boxes or some other black boxes which may be very hard to implement in practice. Such algorithm was missing in literature. And the state of the art before our algorithm was an algorithm by a software called Short Loop, which was implemented by Tamalde and his group, but that works for general complexes. So our algorithm basically derives its idea from two lemmas. Before describing them, I'll quickly give one definition. So a minimum one cycle basis of a graph is very similar to a minimum one homology basis for a simplicial complex, but slightly different. So let's say I'm given a weighted graph. I have a weight function on the edges, which is connected, let's say. So I have e minus v plus 1 edges to it. So then I'll say that a collection of cycles is a minimum cycle basis for this graph G if this is a basis for the cycle space of the graph. And of course, it minimizes the sum of the weights of the cycles. So I'll call that a minimum cycle basis. So minimum cycle basis for, let's say, this triangular wireframe would be ABC, ACE, CED, assuming that we have unit weights on these edges. Now, for a complex, for a simplicial complex, I can compute a minimum cycle basis as follows. I can take the complex, I can compute the one skeleton of the complex, and then I can compute the minimum cycle basis of that one skeleton of the complex, which is just a graph. So our first observation is as follows. So let's say I have a minimum cycle basis from B1, minimum cycle basis for the one skeleton. And let's say B1 to BQ are basically cycles which are boundaries, and C1 to CP are cycles which are non-boundaries. And assume furthermore that C1 to CP, these cycles are arranged in increasing order of weight. So then the first observation is that I can always find a minimum homology basis where zeta 1 is equal to C1. That is always possible. And the second lemma, which is in some sense a repetition of the first lemma, states that given a minimum cycle basis, if I consider these cycles C1 to CP, which are the non-bounding cycles, then I can compute a minimum homology basis from minimum cycle basis in a greedy way. So first I'll pick C1, then I'll pick the next cycle in this sequence, which is independent of the cycles picked up thus far, and is also a non-bounding cycle. So in a sense, the minimum homology basis is a weighted metroid in the minimum cycle basis. And so a very fast greedy selection algorithm can help us compute a minimum homology basis, provided we have a minimum cycle basis. Now, why have we chosen this route? Well, the minimum cycle basis is a well-studied problem in graph theory. It has been studied independently of the minimum one homology basis problem, and there are fast algorithms that compute the minimum cycle basis of a graph. So in particular, there is an algorithm by Kavita, which is very fast, that computes a minimum cycle basis. And then from minimum cycle basis, we can compute a minimum homology basis by what I've just described. The selecting a minimum homology basis from the minimum cycle basis can be reduced to finding a column rank profile of a boundary matrix. The column rank profile algorithm by Jan Rod, which is a very fast algorithm, can then be used, which gives us a nice theoretical complexity. Furthermore, it's a result by Amaldi that the minimum cycle basis, or rather it follows from a result by Amaldi, that a minimum cycle basis is sparse in some sense. And so while doing the rank profile algorithm, it turns out that we can do a reduction of a sparse matrix, which makes it quite fast in practice. So here I'll just show some experimental results on our algorithm. The software is available for free use. So here we have some real world examples. Some particular examples are the zeolite materials. The zeolite materials have these pores in them, which have often interesting physical properties, or which determine physical properties of that zeolite. We can see how minimum homology basis tightly or neatly captures these cycles. They can then be used for further visualization, etc. Okay. So that concludes our algorithm on the minimum one homology basis. As described before, in the simplex weighted simplex count measure, the other flavors of problems are NP hard. So therefore, we turn to the L2 measure. And we consider the minimum homology basis problem, the localized homology representative, and the minimum persistent homology basis problem under the L2 measure. Similarly, as defined before, just the weight function is now the L2 radius of a chain. So when it comes to the related work, we are discussing three flavors of problems. Yeah. So there is this algorithm by Chen and Friedman, where they also consider a minimum bounding ball of a simplex, but they consider a geodesic ball. So the metric that they use is basically the geodesic distance on, let's say, a manifold. Whereas here the distance that we are considering is the Euclidean distance, because we have the added assumption that the complex is embedded in a Euclidean space. So this was the algorithm by Chen and Friedman. Unfortunately, the geodesic ball measure makes the problem NP hard. Like, they have a heuristic, but there are no guarantees under this measure. Then there is lexicographic optimality, under which there are nice theoretical properties, but again, maybe from a practical viewpoint, this measure is not very useful. Finally, Liu Li et al., they use linear programming, but they consider homology in Q coefficients. And again, it's not homology in Z2 coefficients. Z2 coefficients has the benefit of being really nice, interpretable for practical purposes. Finally, there is the algorithm by Day et al., where they talk of computing minimum persistent homology representative under the weighted simplex count. They show that it is NP hard, and they basically develop a heuristic that computes a minimum that computes a persistent homology representative in dimension 1, albeit with no theoretical guarantees. The software Purse loop is an implementation of their algorithm. Now, when it comes to the L2 measure, we claim that it allows for these problems to be tractable. And why is that so? So let's say I have a cycle zeta in a complex K. Let's say its L2 radius is delta. So then one of the lemmas in our paper says that I can always find a subset of vertices U of the vertex set of Vk such that the circumsphere of this subset of vertices is basically the minimum bounding ball of zeta. So the minimum bounding ball is always going to be a circumsphere of some subset of vertices. Now there are only a polynomial number of spheres to check. Well, if my complex is embedded in Rd and assuming that all the points are in general position, the sphere SD minus 1 requires D plus 1 points to be defined. So the number of the candidate number of candidate circumspheres to check is basically NC D plus 1, which is a polynomial in N. But this can be quite hard to check because for large values of D, it is a very big number, even though it's polynomial. So a simple observation says that we need not consider all possible bounding balls. We can only restrict ourselves to bounding balls which are centered on the vertices of my complex K. So an example would be, let's say I have a triangle ABC, its minimum bounding ball is its circumsphere. But if I say I'm going to only consider balls whose centers are at the vertices of my triangle ABC, then although I get a worse bounding ball, the radius of my approximate or worse bounding ball is always going to be at most twice the actual L2 radius. So what we do in our practical implementations is that we mostly consider a too approximate version of the problems under the L2 measure, and by considering spheres which are only centered on the vertices of the complex K. So in the interest of time, I'll only describe very briefly the localized homology representative problem. To recall what it is that I have a cycle zeta, and I want to find out the smallest representative of its homology class under the L2 radius. As described before, I'm not going to check all the circumspheres. Instead, I'm only going to consider vertices which are centered on, instead I'm only going to consider these balls which are centered on the vertex of the complex K. The complex K comes with an embedding in a Euclidean space Rd. Now for each vertex V, I compute the smallest sphere, which basically has a representative of this input homology class, and then I return the smallest over all the vertices V. The non-trivial part is for a vertex V, how do I compute the smallest sphere, which basically has a representative of zeta. So in a very intuitive way, we start with a vertex V, and then we consider distance from the vertex V. And so if basically we filter the complex K based on the distance on the vertex V. So you can think of it as a ball that starts from the vertex V and slowly grows. And then we use certain persistence-based ideas to find out what is that radius when I have encountered a representative of this class zeta. And the smallest, and the moment I slowly grow the radius, and the moment I come up with a representative of zeta, I stop there. And I repeat this process for all the vertices of my complex K and return the radius. So that I know will give me a too approximate L2 radius. Now the other problems, which is the minimum homology basis problem and the localized persistent homology representative problem, they kind of use similar ideas, but I'm not going to describe them over here. Instead, I'm going to just look at how the L2 measure performs in real life data. So this is the minimum homology basis, but computed with the L2 radius. So we can see how the L2 radius kind of nicely captures the cycles in some of these data sets. Yeah, this is the mother and child data set. This is a wheel with many spokes. Then there is the homology localization problem. So, so the cycles in red for each of these data sets are basically some generic cycles. Our goal is to find out the smallest representative of that cycle. So we can see over here that the cycle in blue, let's say, is even though we are considering a 2 approximate algorithm only, at least visually we can say that we get much smaller and neater cycles compared to the generic cycles. This is under the L2 measure. This is the smiling Buddha. Finally, when it comes to persistent homology representative under the L2 radius, so this is a specific example where we have taken a Lorentz 63 point cloud data set, and we've considered a RIPS filtration of it. Here we're showing representative of the top 2 bars. These are important in some weather data simulations. Right. Here we show 2 more examples. One is a Lorentz 63, but generated with a different parameter setting, and another is a Lorentz 96. So the cycle in red over here is a cycle which is computed by Peirce loop. Peirce loop, recall, is the algorithm by Tamalde, which computes a heuristically minimum heuristically minimum representative of a bar. But the measure that they consider is the sum of the weights of the edges, whereas the measure that we consider is the L2 radius. But even though we are considering 2 different optimality criteria, we see that our cycle, at least visually, is smaller than their cycle. And this is for Lorentz 96. Again, this is the top bar for the data. The cycle in green is a cycle that we compute. The cycle in black is the cycle Peirce loop computes. We are computing a smaller cycle. Yeah, finally, I want to acknowledge my collaborators. So I collaborate with Abhishek Rathore, and who is currently at Ben-Gurion, Israel. And Vijay Natarajan is my advisor at IISc. Yeah, thank you. My thanks to ICMDD for inviting me. And special thanks to Professor Vinod Kumar for the invitation. Okay. Thank you. That's all I have. Yeah, I'm open to questions.
Any question from the audience?
Sir,
Yeah.
you have mentioned about some of the softwares here. So how is the function? Like we input some data, it will show the smallest loop containing.
Right. So, right. So, yeah. So, fast loop is our software. So here you can feed any simplicial complex to it. It works for all complexes, and it will return you a minimum 1 homology basis. So it will return all the nice tight cycles to it. And there is a way to visualize the cycles afterwards. So there are softwares like ParaView, MeshLab, where you can then take those cycles and you can represent it, which is basically how we have generated these images.
So the input should be complexes.
The input should be a simplicial complex, weighted simplicial complex. Yeah. No, for this algorithm requires a complex to be fed to it. So if we have a point cloud, we have to generate a complex and then feed it. Weights, it can be any weights. It's a user provided weight. If nothing is provided, then we can take the Euclidean distance between the 2 vertices to be the weight. That is typically how it works. And other software, there is this software called Peirce loop, which computes minimum persistent homology basis. This is by Tamalde and his group. This is again freely available. One has to email Tamalde to get access to it. Like our algorithm, will release the software sometime, probably next month. That's all.
Thank you.
Yeah, thank you.
Any other question? Okay, if there is no other question, so I'd like to thank the speaker again.
Thank you.
I invite Amit sir to give away the memento to Amritendu-Shekhar. Thank you, Amit sir, for chairing the session. Next, we will have the contributory paper presentation. We will now begin the contributory paper presentation session. I invite A.R. Rajan sir to chair the session.
Good evening. So we are starting the short communication session. So the first speaker is Rohit Nageshwar. So he will be speaking on weaker form of spectral decomposition. Rohit.
Well, thank you for this opportunity. So in this talk, we talk about weaker form of spectral decomposition. So I start with topological dynamics. So first of all, what is dynamical system? So in dynamical system, we generally study the changes that occur over time in a physical and artificial system. A topological dynamical system consists of a topological space and a continuous self map F on X. So this is the definition of generally accepted definition of topological dynamical system. This is an example of topological dynamical system where X is a two-dimensional Euclidean space and F is a linear map induced from this diagonal matrix lambda U. In topological dynamical system, the development considered, early development considered by the work of Henry Poincaré and G.D. Birkhoff. In mid-20th century, topological dynamical system and topological dynamics started to take shape with the work of Stephen Ismail, Rufus Bowen, and David Ruella. Stephen Ismail is known for his work on Ismail horseshoe map and spectral decomposition theorem, so which we're gonna discuss here. So this is the picture of Stephen Smith. Okay, so before going further, first we recall some terminologies. So throughout this talk, our F will be a continuous map, X be a matrix space. XZ denote the product space with product topology of infinite copies of X. If F is surjective map, then this set XF will denote the inverse limit space induced from the map F with subspace topology from XZ. And here sigma is the shift map which shifts every point of the sequence Xn one step to the left. We say that F is topologically transitive if from every open set U, you can visit any other non-empty open set under the positive action of F. And topological mixing can be understood as the permanent regional transitivity. In other words, topological transitivity says that you cannot decompose a system into two invariant open sets. Okay, a point X is said to be non-running point if for every neighborhood U of X, you can revisit U under the positive action of F. This is important because of its recurrent behavior. And we denote the set of non-rounding point by omega f. A point x is said to be chain recurrent point if for each delta, you can find a delta pseudo orbit from x2 itself. And we denote the set of chain recurrent point by CRF. And we already know what is the periodic point. Its orbit return to itself after finite iteration. Okay. Another important property in the topological dynamical system is expansivity, introduced by Uch in 1950 in his paper Unstable Homomorphism, published in Proceeding of American Mathematical Society, which says that orbit of any two different point can be separated a prefix distance apart. Another important property is shadowing property, which was introduced by Onoso in 1967 and independently studied by Bowen in 1975, which says that any pseudo orbit can be approximated by true orbit. These two properties have a crucial role in development of theory of dynamical system, and in particular spectral decomposition theorem. So the spectral decomposition theorem was proved by Stephen Ismail in 1967 in his paper Differentiable Dynamical System, published in Bulletin of American Mathematical Society, which says that the non-rounding set of an axiom diffeomorphism but sir, if this half part is missing.
Slideshow is not coming.
Yeah.
Okay.
Okay. So Smail proved that the non-rounding set of axiomate diffeomorphism of a smooth Riemannian manifold can be decomposed into union of finitely many pairwise disjoint closed sets on which the diffeomorphism is transitive. Later, his student Rufus Bowen proved in 1971 that each closed invariant set obtained in Ismail's decomposition theorem can be further decomposed into pairwise disjoint closed sets such that the restriction of some iterate of the map to these sets is topologically mixing. It is known that Onoso diffeomorphism are particular case of axiomate diffeomorphisms. And also each Onoso diffeomorphism is expansive as well as shadowing property, which motivated Aoki in 1983 to prove the Ismail's result for homomorphism on compact matrix spaces having expansivity and shadowing property. Recently, another form of expansivity has been introduced by Lee et al. In the paper Asymptotic Expansivity published in Journal of Mathematical Analysis and Application, which says that if orbit of 2 points remain a prefix distance close at each instant of time, then those orbits are asymptotic to each other. They also introduced the biasymptotically expansive homomorphisms for which both f and its inverse is asymptotically expansive. And they characterize the property of axiomate diffeomorphism, which says that the non-rounding points coincide with the closure of periodic point for axiomate diffeomorphism. So they have proved it for asymptotically expansive homomorphism having shadowing property on compact matrix spaces. And finally, they prove the spectral decomposition theorem. So this is the mathematical statement of spectral decomposition theorem, which I just stated. Okay, so if we talk about the continuous surjective map, we have backward orbit. We can think of backward orbits. So with this idea, Aoki and Hirade studied a form of expansivity for continuous surjective map. So we have two sequences, x and yn, which are actually element of xf. So we can consider it orbit of f. And if these two orbits remain delta distance close at each instance of time, then this orbit would be shared. So this is the C expansivity they have introduced. Now, interesting question is, what happened to these orbits? Like asymptotic expansivity says that if two orbits remain delta distance close, then they are asymptotic, forward asymptotic. And if their backward part remains delta distance close, so they are backward asymptotic. So with these idea, we have thought that maybe for the continuous surjective map, this is also possible. First of all, we have constructed an example which is not C expansive, but behave like a biasymptotically expansive map. So our space X will be the union of this kind of sets, and our map is this. So we have this phase portrait for that map. If you see, our space is union of X0, X1, X2, and Xm with the subspace topology from R, and our map is mapping every point in the under the positive action to right side and under the negative action to the left side. So if you see, you take any 2 point, their orbit approaches to 1. And if you take any 2 point, their backward orbit approaches to -1. And that's why these behave like a biasymptotic expansive map. But this map is not C expansive, because the way I have constructed this example, for every delta positive, you can find a point which is a delta distance close to -1/2 and remain delta distance close. So we have two orbits for every delta which are delta distance close, but they are not same. So this is not C expansive. This motivated us to introduce the notion of biasymptotic C expansivity. So likewise, we have defined it if the two forward part of two orbit remain prefix distance close, then they are asymptotic, and if the backward orbit remains C distance close, then they are backward asymptotic. So we have studied the relation between various notion of expansivity on compact matrix spaces. So we observed that for continuous surjective map, C expansivity implies biasymptotic C expansivity, but converse is not true by the previous example. And we also observed that for homeomorphism, biasymptotic C expansivity and biasymptotic expansivity are equivalent, and C expansivity and expansivity are equivalent. Lee et al. Proved that expansivity implies biasymptotic for expansivity for homeomorphism, but converse is not true, because you can take an example of fx is equal to x square and close interval 0, 1. This is as a biasymptotically expansive, but it is not expansive because the intervals do not admit expansive homeomorphisms. We also observed that if F is biasymptotically C expansive continuous surjective map on compact matrix species, then the shift map on the inverse limit space induced from F is biasymptotically expansive. And see the characterization of examined diffeomorphism for these map having shadowing property on compact matrix spaces. And finally, prove the spectral decomposition theorem for biasymptotically C expansive continuous surjective map on compact matrix spaces with shadowing property, which says that the non-rounding set can be decomposed into finitely many pairwise disjoint closed sets such that restriction of the map to these sets is topologically transitive. Further, each set can be decomposed into pairwise disjoint closed set such that restriction of some iterate of the map to these sets is topologically mixing. Well, this work has been recently published in Journal of Mathematical Analysis and Application with it is co-authored with Dr. Khan and Professor Das. So these are some selected references. So yeah.
Comments?
Can you give an example of biasymptotic C?
Okay. The example I have just this one. Okay, this one is an example. This is interesting because it is not C expansive.
Exact function?
Yeah. This is exact function. So I can.
Can you give a simpler example?
Sorry, simpler example.
Yeah.
Okay. You can take this map simply. Fx is equal to x square. Sorry?
Any increasing function?
Not any increasing function, just. So this is Fx is equal to x. So this is the simplest example because this is this is 0 is fixed point, 1 is fixed point. Okay. Now if you take delta to be half and any 2 point whose orbit remain delta distance. So the interesting thing is except one, orbit of every point approaches to 1. So this is asymptotically expansive. And there are no point, sorry? So C they only use for I think continuous map because I'm not sure because I searched for that why they have used C, but there is very little work on C expansivity.
Okay. So thank you, Rohit Nageshwar. Let's thank the speaker. Now I invite the next speaker, Rachel Paul. She'll be speaking on radio contra harmonic mean labeling. Yes.
Hello. Okay, my topic is radio contra harmonic mean labeling. So Chartrand and Harry were motivated by the regulation for channel assignments of FM radio stations to introduce the radio labeling of graphs. The radio networks can be considered as a graph in which vertices correspond to transmitter locations and two vertices are adjacent if the location of the radio stations correspond to the vertices are close. So the main objective is to label vertices of this graph with minimum span where the label given to the vertices determine the channel on which it transmits. So Sadish Narayanan and Kala introduced the concept of radio mean labeling. From the detailed survey of graph labeling, we found that there are mean labeling such as radio mean labeling, radio geometric mean labeling, radio odd mean labeling, radio even mean labeling, etc. So motivated by the above result, we introduced a new type of labeling called radio contra harmonic mean labeling. So these are the preliminaries. The contra-harmonic mean of a set of positive numbers is defined as the arithmetic mean of square of numbers divided by arithmetic mean of numbers. The Helm graph is created by connecting a pendant edge to each rim vertex of a wheel. The gear graph is a wheel graph in which a vertex is placed between every two adjacent vertices of the outer circle. The graph that results from connecting each pendant vertex to its center from Helm is a flower graph. A lotus inside circle graph is a graph obtained from the cycle Cn and a star Kn with central vertex V0 by joining each Ui and Ui plus 1 mod n. And a sunflower graph Sfn is a graph obtained from wheel graph with the vertex set U, x1, x2, etc. xn and the extra vertices y1, y2, etc. yn with the given edge set E. So this is a radio labeling. A radio labeling is a one-to-one mapping f from v of g to n satisfies the condition d of uv plus the ceiling of f of u minus f of v greater than or equal to 1 plus diameter of g for every uv element of v. This one is radio mean labeling. Here we replace that function with the mean, that is d of uv plus f of u plus f of v divided by 2 greater than or equal to 1 plus diameter of g. So the radio mean number of f or Rmn of f is a maximum integer assigned to any v element of g under this mapping f. Further, the radio mean number of g denoted by Rmn of g is the smallest value of Rmn of f taken overall radio mean labeling f of g. So this is our new labeling, radio contra harmonic mean labeling. So a radio contra harmonic mean labeling is a one-to-one mapping f from v of g to n satisfies the condition d of uv plus ceiling function of f of u square plus f of v square by f of u plus f of v greater than or equal to 1 plus diameter of g for every uv element of v. So the radio contraharmonic mean number of f or RCHMN of f, the maximum integer assigned to any vertex v of g under this mapping. Further, the radio contraharmonic mean number of g denoted by RCHMN of g is the smallest value of RCHMN of f taken overall radio mean labeling of f. So from this result, it is obvious that the radio contraharmonic mean number of a graph is always greater than or equal to the order of a graph. And if the radio contraharmonic mean number of a graph is same as its order, then it is called radio contraharmonic mean graceful graph. So these are some results. If G is a graph of order n greater than or equal to 1 and diameter d equal to 1 or 2, then radio contraharmonic mean number of that graph is order itself. That is, it will be a radio contraharmonic mean graceful graph. The radio contraharmonic mean number of a gear graph Gn is 2n plus 2 for n greater than or equal to 4. The radio contraharmonic mean number of Helm graph 2n plus 1 for n greater than or equal to 3. For spider graph RTNN is 2n plus 1 for n greater than or equal to 4. For flower graph FLN is 2n plus 1 for n greater than or equal to 3. For lotus inside circle graph is 2n plus 2 for n greater than or equal to 8. And for sunflower grass SFN is 2n plus 1 for n greater than or equal to 6. These are my results. These are my references. Thank you. Okay.
You have written the proof.
Yeah.
Okay, that's all right.
Actually, we want to define that function.
Okay. Now, what is the advantage of this labeling over the existing labelings?
Okay, what I am planning to do that is the radio mean labeling have application cryptography for passing messages. So I think that contraharmonic mean is will give a secure key, more secure key. So that's my aim to prove. Right. Motivation. So the last paper by K and Meera, they have proved one key for secure networking.
Okay, fine.
Oh, yeah, it's my reference. That's the first paper of radio labeling. That's the first paper of radio mean labeling.
Okay, fine.
Thank you.
So let's thank the speaker. Thank you. The next speaker, Mithunas, he'll be speaking on F domination in direct product of graphs. Mithun.
First of all, I would like to thank the organizers of this conference to give me the opportunity to present my manuscript. So my name is Midhunas. I am assistant professor at Government Polytechnic College, Punalur. I have done this work under the guidance of Dr. Raji Pillakat, retired professor at University of Calicut. So my title of my work is F domination in direct product of graphs. We all know about domination. Let G be a graph. Then a subset D of V is said to be a dominating set if every vertex of V minus D, that's a complement of D, is adjacent to at least one vertex in D. For example, in this picture, the red colored vertices are adjacent to every vertex in adjacent to all black colored vertices. That is, the complement of the red colored vertices are the black colored vertices. That each vertex in complement is adjacent to red colored vertices. So these two red colored vertices form a dominating set. It is easy to note that the domination number is 2 for this graph. So Next is total dominating set. Let G be a graph, then D is said to be a total dominating set if every vertex is adjacent to at least one vertex in D. T is said to be a total dominating set if every vertex in G is adjacent to at least one vertex in D. For example, look at this. We already said that the red colored vertices form a dominating set, but it is not a total dominating set because both red colored vertices are not adjacent to each other. Therefore, these cannot form a total dominating set, but with the red colored and yellow colored vertices, we form a total dominating set. Okay. Next, we define F dominating set. The concept of F domination was introduced by Manjuraj and others. The definition is, let G be a graph and F be a family of subsets of V, whose union is full set V. Okay. A dominating set D of G is called an F dominating set if D intersection F is not equal to empty for all F belongs to F. For example, consider C3. Here the vertices are V1, V2 and V3. With a family of vertices, first set is V1, V2 and second set is V3. We choose a subset D, D is equal to V1, V3. We can easily see that V1, V3 set D is equal to V1, V3 is a dominating set. But D intersection F1 is equal to V1, therefore non-empty, and D intersection F2 is equal to V3 and it's also non-empty. Therefore, gamma F of C3 or K3 equal to 2. Next, we define direct product of two graphs. Let the direct product of G cross H of two graphs G and H is a graph with the vertex set V of G cross V of H, with where V of G cross V of H is equal to U comma V, U belongs to V of G and V belongs to V of H. And any two vertices U1, V1 and U2, V2 are adjacent whenever U1, V1 is an edge in U1, U2 is an edge in E of G and U2, V1, V2 is an edge in E of H. This is an example for P2 cross K3. Next is we define total F dominating set. Let G be a graph and D be a subset. D be a total dominating set and D is said to be a total F dominating set if each F intersection D must be non-empty for F belongs to the family. Now also for my next result, I define some product of F1 be a family of sets such that F1 is equal to A1, A2, etc. to AM, and F2 is equal to B1, B2, etc. to Bn. Then F1 cross F2 is equal to A cross set of all A cross Bj, where 1 less than or equal to I less than or equal to M, comma, 1 less than or equal to J less than or equal to N. Then my first result is, let G and H be any two simple graphs with no isolated vertices. Let F1 be the family of subsets of G and F2 be the family of subsets of H. Then gamma F1 cross F2 of G cross H less than or equal to gamma T F1 of G into gamma T F2 of H. Next theorem is, let G be a graph, simple graph, and H be a simple graph with no isolated vertices. Let F1 be the family of subsets of V of G and F2 be the family of subsets of V of H. Then gamma of F1 cross F2 of G cross H less than or equal to gamma F1 of G into cardinality of V of H. Using this previous results, we get a corollary. Let G and H be any two graphs without isolated vertices. Let F1 be the family of subsets of V of G and F2 be the family of subsets of V of H. Then gamma F1 cross F2 of G cross H less than or equal to minimum of gamma F1 of G into cardinality of V of H, comma, cardinality of V of G into cardinality of gamma F2 of H, comma, gamma T F1 of G into gamma T F2 of H. Next, we define some term like IS of D, which is the, isolated vertices. Let G be a graph and D subset of V of G. Then IS of D is equal to set of all X belongs to D, such that N of X are the neighborhoods of X. Intersection D must be empty. And also we define pi1 of f is equal to, that is a projection of f, is equal to set of all u, uv belongs to f, and pi2 of f is equal to set of all v, uv belongs to f. Next result is, let G and H be any two simple graphs. Let script f be a family of subsets of V of G cross H. Then gamma f of G cross H less than or equal to minimum of cardinality of D1 minus IS of D1 into cardinality of D2 minus IS of D2 plus cardinality of IS of D1 into cardinality of V of H plus cardinality of V of G into cardinality of IS of D2 minus cardinality of IS of D1 into cardinality of IS of D2, where the minimum is taken over all pi1 of f dominating set D1 of G and pi2 of f dominating set D2 of H. Next theorem is, let G and H be any two graphs without isolated vertices. Let script f1 be the family of subsets of V of G and script f2 be the family of subsets of V of H. Let D be an f1 cross f2 dominating set of G cross H. Then D1 is equal to set of all u. UV belongs to D is an f1 dominating set in G. Let G and H be any two graphs without isolated vertices. Let f1 be the family of subsets of V of G and f2 be the family of subsets of V of H. Then gamma f1 cross f2 of G cross H greater than or equal to maximum of gamma f1 of G comma gamma f2 of G. This is a lower bound, and in next example we show that the lower bound is, and the above theorem is sharp. We choose G is equal to P2 and H is equal to K3. Then the direct product P2 cross K3. Here gamma f1 cross f2 of G cross H is equal to gamma f1 of G equal to 2. So in this case we attain the lower bound. Next we define projection pi1 of D subset of V of G cross V of H. Then pi1 of D is equal to set of all x, xy belongs to D. Also pi2 of D is equal to set of all y, xy belongs to D. Similarly, if u belongs to pi1 of D, we can define du. Du is equal to set of all v, uv belongs to D. Using these previous conditions, we define a necessary and sufficient condition for D becoming a dominating set in direct product of graphs. Let G and H be any two simple graphs. Let D contained in V of G cross V of H. Then D is a dominating set of G cross H if and only if it satisfies the following conditions. First condition is pi1 of D must be a dominating set. And second condition, if U belongs to V of G and U not an element of pi1 of D, then union X belongs to N of U intersection pi1 of D. Dx is a total dominating set in H. Third condition is if U belongs to V of G intersection pi1 of D and U is isolated in pi1 of D, then du is equal to V of H. And the final condition, if U belongs to V of G intersection pi1 of D and U is not isolated in G, then du complement is dominated by union of set of all x belongs to N of U intersection pi1 of D dx in H. Using this result, we prove the necessary and sufficient condition for a set D to become a F dominating set. That is, let G and H be any two simple graphs and F be a family of subsets of V of G cross V of H. Then D subset of V of G cross V of H. V of G cross H is an F dominating set of G cross H if and only if D satisfies the following conditions. First condition is pi1 of D must be a pi1 of F dominating set in G. And the second condition, if U belongs to V of G and U not an element of pi1 of D, then set union of X belongs to N of U intersection pi1 of D. Dx is a total dominating set of H. And third condition, if U belongs to V of G intersection pi1 of D and U is isolated in pi1 of D, then du is equal to V of H. Third condition, if U belongs to V of G intersection pi1 of D and U is not isolated in pi1 of D, then du complement is dominated by union X belongs to N of U intersection pi1 of D dx in H. And the final condition, for each F belongs to F, union X belongs to pi1 of F intersection pi1 of D dx intersection pi2 of F must be non-empty. Next result, we discuss about a necessary and sufficient condition for a set D to become a total dominating set. Let G and H be any two simple graphs with no isolated vertices. that D contained in V of G cross V of H. Then D is a total dominating set of G cross H if and only if it satisfies the following two conditions. First condition is pi 1 of D must be a total dominating set in G. And second condition, for each U belongs to V of G, union X belongs to N of U intersection pi 1 of D, dx is a total dominating set in H. We using the previous result, we construct other result for D to become a total F dominating set. Let G and H be any two simple graphs with no isolated vertices. Then D contained in V of G cross V of H is a total F dominating set of G cross H if and only if it satisfies the following conditions. First condition is pi 1 of D is a total pi 1 of F dominating set in G. And the second condition, for each U belongs to V of G, union X belongs to N of U intersection pi 1 of D, dx is a total dominating set in H. And third condition, for each F belongs to script F, union X belongs to pi 1 of F intersection pi 1 of D, dx intersection pi 2 of F must be non-empty. Okay, thank you. These are my references.
Okay. So is there any special results depending on the choice of the family? For example, you make a special choice for the family. Okay. Suppose it is singletons.
I have done. I am trying to do it. Some zero divisors graphs with the family of prime ideals.
Any special context
Okay.
in which these F will be very, very relevant?
Okay. If we choose the family as neighborhoods of vertices, that is N of U, U and adjacent vertices of U, we will get the dominating F dominating set is equal to the dominating set itself. There are similar kind of results also.
Okay, thank you. Let's thank the speaker. Our next speaker is Jeeva Jose. She will be speaking on unmet properties in the persistence diagrams, a comprehensive exploration with illustrative examples. Jeeva Jose.
Good evening to all. So as Sir told, the topic of presentation is unveiling metric properties in the space of persistent diagrams, a comprehensive exploration with illustrative examples. So a persistent diagram has an integral part in data analysis. So the whole picture starts from building a structure on data. For that, initially we want simplices as building blocks. So simplices, there are different dimensions, 0 dimension, 1 dimensional, 2 dimension, and so on. And once we have simplexes, we can construct simplicial complexes over them under certain conditions. So there are different ways to construct simplicial complexes. They are Delaunay complex, check Rips complex, Weakness complexes, etc. So once we have a complex, then we can define a P-chain group. P-chain group is a combination of P simplexes. Then once we have P group, we can have a homomorphism from P group to P-1 group, and that is called a boundary map. And any chain with a 0 boundary is called a cycle. And by fundamental lemma, we have all boundaries are cycles. So the essential question how to distinguish from between boundaries from that of real cycles leads us to the homology group. And homology group helps us to identify the unlike holes of a space. And the rank of pth homology group is called the pth Betti number. Now, subcomplex of a simplicial complex is a simplicial complex that lie inside a simplicial complex. So if we have a structure like this, that means one complex inside another, we can call that structure a sequence of complexes as filtration. So once we have filtration, there is an inclusion map from Ki to Kj, since Ki is a sub-complex of Kj. And this inclusion map will induce a homomorphism, Fpij, from the pth homology group of Ki to the pth homology group of Kj. So we can have a sequence of homology groups like this based on that inclusion map. And the pth of persistent homology group HPIJ is defined as the image of FPIJ. Now, and the corresponding Betty numbers are the rank of those group HPIJs. So persistent homology group gives information about the classes that are born at the stage I and die at the stage J. So here we can see the definition of what is meant by born and what is meant by death. A homology class gamma is said to be born at stage I if it does not belong to the image of FPI-1 I map. And it is said to, the class that born at ith stage is said to be is said to be died on jth stage if it does not belongs to HPI-1 J-1, but it belongs to HPI-1 J. So this figure illustrates clearly when does that class gamma takes birth and die. So persistent homology class, the persistence of class that born at I and dies entering J is J-1. That means the time span of that particular class is called its persistence. Now, barcode is one of the graphical way or visualization of these information. So barcode basically, what barcode basically do is that it gives information of how long a particular homology class persists in a data. So here we can see on same data, we are increasing the radius of the board and we get a filtration, and corresponding to each filtration, we are getting new homology classes, and they are mentioned in different lines. That is, 0-dimensional classes are mentioned in the red line, and 1-dimensional classes are mentioned in the green line, and so on. And this another way of representing barcode is persistent diagram. So if an interval that start at I and ends at J is represented as a pair IJ, then it is called a persistent diagram. And how many such points exist? That is the multiplicity of that point. And that is represented as mu Pij and can be calculated by this formula. And the persistent diagram, so we can define a persistent diagram as a multiset of point Ij in R square with the multiplicity mu Pij. So this is the visualization of how we can convert a barcode to its corresponding persistent diagram. And fundamental lemma of persistent homology states that the pth persistent Betty number can be calculated in this way. That means we will find the total number of points in the upper left portion of the diagram. Now, in this particular paper, persistent diagram is theoretically stated, and the definition is like this. First, we consider this particular set, that is, set of all points in R2 that lie above the diagonal. And if it that space R2, and a persistent diagram is defined as a countable map from this set to as a map from a countable set I to R2. So if D1 and D2 are two persistent diagrams, then the partial matching between these two diagrams is defined as in this way. That is, we will have an I1 dash, I2 dash, and a function f. I1 dash will be a subset of I1, I2 dash will be a subset of I2, and f will be a bijection from I1 dash to I2 dash. So this is a partial matching between two persistent diagrams. And so D infinity is the maximum metric, and that is the metric we are going to use here. So once we have a partial matching, the cost of partial matching is defined like this. That is, it is the sum. First, we will take this sum, that is the distance between matched pairs. Along with that, we will add the distance between the unmatched pair and the diagonal. Similarly for the other diagram also. And we'll take the power p, and the whole sum is given the power 1 by p. That is the pth cost of partial matching. If p is equal to infinity, we will get the cost infinity. That means there we are giving the maximum of supremum norm. So from this cost of partial matching, we get two kinds of distances. One is was-sustained distance, another one is bottleneck distance. And P was-sustained distance is defined as the infimum of the cost of partial matchings. And bottleneck distance is defined as the infimum of the cost of partial matching when P is equal to infinity. So now we have a set of metrics, a set of persistent diagrams and a metric associated to it. So we are getting a metric space of persistent diagram. So our interest of research is to get the properties of these metric spaces, and these are some of the existing properties that is already found in literature. And this is some of the application we are trying to do. That is, we are going to make a comparison between the CT scans of brain with and without tumor and make an analysis. So we can clearly see that the persistent diagram corresponding to the image without tumor and with tumor is significantly different, and the difference can be calculated with the metric we defined earlier. And this one is the comparison of MRI scans of non-demented and mild demented. This is to predict the dementia of people. And here also we can see there are significant difference between the persistent diagram obtained. And this is the CT scan of lungs without tumor and with tumor. And okay, now these are the some properties of metric spaces, that is gap, that we are going to see next, that is gap, spread, and reciprocal means singularity. So what we are intending to do is we make use of these characters or features to classify the persistent diagram we got earlier. So first one is a gap of a metric space. So let XD be a metric space and BXR be the closed ball in X centered at X. So for 2 points x, y in X, we define the hyper distance between X and Y as 2 into infimum of the radius R, such that there exists a ball around a point Z, such that X and Y is belonging to that ball. And that is HD of hyper distance between X and Y. After getting hyper distance, we will calculate the LiPo distance. LiPo distance is defined as the difference between hyper distance and the original distance between those 2 points. So the gap is defined as the supremum of LiPo distance. This is one of the characteristics that we are going to compare for the application we told earlier. And another one is spread of metric space. Spread for a metric space X with a metric D, spread is defined as summation over X belongs to X, 1 by X dash belongs to X. That means first we will find the similarity between the points, and we will take the summation, inverse it, and take the whole summation. So the inference that we get from the spread of a metric space is that if the distance between the points are sufficiently small, then we can consider them as same or single cluster. As far as the distance between the points increase, they can be grouped to separate clusters. So basically this E naught X lies between 1 and n, where n is the number of points in the metric space. So this is theorem that states the properties of spread. It lies between 1 and n. As t increases, E naught Tx also increase. And as t tends to 0, E naught Tx tends to 1. And as t tends to infinity, it tends to n. So, and it will be always less than or equal to effective diameter of X. That means effective diameter means this is a maximum distance between the present between the points of the space. Another characteristic is reciprocal mean similarity. Here for a finite metric space X with n points, we will calculate this reciprocal mean similarity for each points. If we are considering the point xi, then its corresponding reciprocal mean similarity is rho I, and is calculated by this formula. And here rho I lies between 1 and n. So what this measure tells us is that if rho I is nearly 1, it means all other points of the metric space are sufficiently close to that point. If it is n, means all points are at a distance, at a particular distance from that point under consideration. So here also rho I lies between 1 and n. So this is an illustrative example. We have 5 points here, and the distance between these points are mentioned in this distance matrix. And we calculated the above set properties, that is gap, spread, and reciprocal mean similarity of that particular example. And our further studies using these characteristics to classify the before said applications. That means the CT scans, MRI scan, everything, and to identify whether the patient is having a disease or not. And these are my references. Thank you.
So you have introduced several metric or distances or parameters. Okay.
Those are already existing.
Okay, that's right. Now, is there any comparison which is more advantageous depending on situations?
Actually, we always need to characterize persistent diagram somehow. Because, we cannot conclude the analysis by finding persistent diagram. We need to characterize it somehow. That's why we picked up these particular characteristics.
Can you identify some of them which are more efficient than the other?
No,
Like
sir.
that?
That work is going on only. Thank you, sir.
So we are coming to end of the presentations. So I thank all the speakers once again. Thank you.
Thank you, sir, for chairing the session. Tomorrow, the first session starts at 9:30. Okay.